Okay, good morning, everyone. Thank you for joining on this very chilly morning. We are grateful that you can be here, even though it's school holidays already. Today we have a very full program, so we're not going to have a lot of administrative talks. I just wanted to say that we're going to do each presentation during the time slot allocated. Afterwards, you're welcome to ask a question using the Q&A function there on the bottom of your screen. You can also use the chat if you wanted to ask a direct question to someone. You can also raise your hand if you wanted to be unmuted and then ask your question live. Very welcome to do that. We have a big attendee list today, and thank you so much for really investing in Metabolomics and really taking your time to be here today. We have about 92 participants currently in the meeting. We hope that you will really get something from this and get what you hope to get when you registered. This is the very first meeting that I know of where DIPLOMICS, the National Metabolomics Platform, Metabolomics SA, and Microsep is working together to bring you the best training that you will ever see. So I think you are assisting us to making history in these collaborations, and we're trying to push these collaborations forward as much as possible. So without any further delay, I'm going to give over to our very first speaker, Mr. 𝗬𝗲𝘁𝗿𝗂𝗰𝗁𝗂𝗔. Louis is a water sales manager at Microsep with over 25 years of experience at Microsep. 𝗬𝗲𝘁𝗿𝗂𝗰𝗁𝗂𝗔 brings a wealth of experience and expertise to his role as the water sales manager. Thank you, Louis. You're welcome to continue.
Appreciate the opportunity. Thank you that I can start off, and I would like.
So, Louis, I can't hear you. I think you're still muted, maybe.
Someone muted me, probably one of my colleagues.
You're just a bit soft, Louis.
Oh. Okay. Can you hear me now?
A bit better, yes.
Better. Okay, I'll get the mic up here. Is that better?
Yes.
Excellent. Okay, sorry guys, thank you. Ilse, thank you for the opportunity. Yes, I have been part of the furniture at Microsep for 29 years now. So it is exciting to see the growth. And without being to do marketing, you know, I am in sales for 29 years. So it's always difficult not talking about products. I think the team, Dylan and Bianca, have put something very nice and specific together that is not product related. But while I've got the opportunity, we have been selling waters for myself for 29 years. Now, waters is currently at a $0.9 billion company, 7,500 employees across the world, and they're sitting at about $300 per share at the moment. So a healthy scenario, which allows them to put a lot of input into research and development. When I started in '95, we launched an alliance system, and I'm happy to say that some of those are still actually operating in the market. Why do I start here? I think one of the highlights for me in '95 as well, besides starting with Microsep, was where Waters bought Micromass. That was entry into the MS market, and I think that's very relevant for where we are today, into the metabolomics and the development Waters had in this field of mass spectrometry, and now grown into the ion mobility and the stuff you'll hear about from my colleague better. Yeah, I think when I started, suppliers were building equipment and selling it to the users. I think we very quickly learned over the years that we need the input from customers before you just design something. And that's where a lot of our new technologies were born, with UPLC, SYNAPT, 𝗬𝗀𝘀𝗀𝗀𝗀𝗀𝗀𝗀𝗀. So very exciting times for us over 29 years. And I'm happy to say that we've even launched a new system in the last week or two at ASMS, and very exciting future, especially in the metabolomics field. Microsep over the 29 years, I think what I always believed in, and I hope to strive with this training and being part of this, is that we really like to do the innovative solution for our customers, and we really believe in world-class service. So that's what we've been standing for over the years, and I hope that we'll be able to fulfill that, especially in this project. We're really excited to be part of it. So I would like to just end off by saying good luck to all the researchers that will be applying, putting forward their proposals, and I look forward to meeting the final 9 people in the face-to-face training in the future, and I hope that whatever the team brings to yourselves, that you can take forward in your research work. Thank you very much, Ilse.
Thank you so much, Louis. We appreciate you being here and taking your time being here, and the support from Microsep in this project. This project was an original idea that came up at Metabolomics SA to share knowledge in metabolomics. And so for that initiative, we have Dr. Lungile Sitole here today. But first of all, I just want to hear if anybody has a question for Louis about Microsep. Sorry. Any questions, any quote requests? Okay, I'm sure the Microsep questions will come in a bit later in the more technical presentations, Louis. Thank you. Okay, so as I said, this is an initiative from Metabolomics SA originally, where we had a lot of discussions. I think this came along for a few months, that we wanted to do a training like this in this format, bringing together a lot of different role players. For that reason, we have Dr. Lungile Sitole today representing Metabolomics SA. Dr. Sitole is currently a senior lecturer and a principal investigator in the Department of Biochemistry at the University of Johannesburg, where she also serves as the director of the 𝗬𝗂𝘀𝗀𝗃 Science Center, which is geared towards the provision of tuition to learners and development of teachers to improve the quality of mathematics and science education in South Africa. Dr. Sitole is also an active member of Metabolomics SA, as I mentioned, and she really has a passion for teaching and learning. Dr. Sitole, thank you for being here today, and we're looking forward to hearing more about Metabolomics SA and the role that you play in the country. Thank you.
Thanks, Dr. Du Preez. I'm going to quickly share my slides. So you can see my slides, right? All right, good morning, everybody. And once again, a warm welcome to today's really interesting webinar. This is one in a series of many. And this one is, of course, brought to you by a solid partnership between Metabolomics South Africa, DIPLOMICS, Noordwes-Universitei's Center of Human Metabolomics, National Metabolomics Platform, and of course, Microsep. So today you're in for a really great treat. There are some really interesting talks on LCMS, and hopefully what you hear today will increase your interest in applying LCMS-based metabolomics. So I am here on behalf of the chairperson of the Metabolomics South Africa Society, and I have been asked to share what it is that we do, the role that we play, specifically in South Africa, and how do you also become part of this network. Okay, so Metabolomics South Africa, or as it's commonly referred to as MSA, was established in 2018. And since then, we are affiliated to the larger organization, which is the International Metabolomics Society. And given this affiliation, we of course share similar goals. And for us as MSA, our goal really is the advancement of the metabolomics field in not only in South Africa, but in the entire African continent. And our missions are really straight. We aim to promote the growth and development of the metabolomics field in South Africa, by extension into all other African countries, to promote and facilitate strong relations and collaborations among scientists doing metabolomics work as well as related fields, facilitate connections between academia and industry, and to foster really strong networking, teaching, information sharing, mentoring, and career opportunities related to metabolomics. Now, if you want to know more about the organization itself and you want to have a look at our chatter, you are more than welcome to visit the website, which is metabolomicssa.co.za. Now, in terms of the membership, so of course what the organization does, we support those doing metabolomics in the country. And the support comes in various ways, and I think you'll see this in the next slide. But in terms of the current membership, so like other organizations, we are really growing, and we are growing really, really fast. So it's quite exciting to see the growth that's taking place within the society. But because in relation to other organizations that are out there, we are still small. So at the moment, we do not charge any membership fees to be part of this network. That will, of course, change in the future as we grow even bigger. And at the moment, we have just over 300 members who have signed up to be part of Metabolomics, which really shows the interest is there. And there are quite a number of people in the country doing metabolomics-related work. Of course, the majority of these members lie in South Africa, obviously because the organization was established in South Africa, but we do have a really strong presence in other African countries. We also then have a strong presence in quite a number of universities throughout the country and various other institutions as well. So this is just to really give you a glimpse of the organization itself. So of course, the leadership is made up of all the institutions that are involved in the society. This is UJ, TUT, Northwest, UNISA, Univen. If I didn't call your university, please don't blame me. It's just too many to mention. And of course, underneath all these institutions, you have various levels and you have various subcommittees. And all of these people, all of these within these committees are really working hard to bring to you trainings and workshops on metabolomics, similar to this one. And all of these people are really working hard to make sure that this organization is a success. Now, this is also a glimpse to just give you an idea of what we've done in terms of webinars, training, and events from inception, which is 2018 until 2023. So I think the organization itself has done quite a lot, given that when you think of the omics cascade, I mean, metabolomics is right at the bottom, right? It's the baby omics. And in South Africa, we're really trying to grow this baby omics. And I mean, many years ago when genomics started, people also, shunned upon it, didn't think it would amount to too much, but look at it now. So that is exactly where we're trying to lead metabolomics as well. And in doing this, we've done quite a lot. The organization has hosted various trainings, webinars, workshops, and one of my favorites is the journal clubs. So if you are interested in knowing what people are doing in the country, in other African countries, in terms of metabolomics, how are they applying it in their research, how to overcome data analysis issues, I would really encourage you to sign up and join in on the journal clubs that are constantly hosted. And yeah, you will see how much work people are doing in this specific field. Now, we do also have a really strong online presence, and a huge shout out to the communication subcommittee for this. I suppose it helps that they're all very young, so they are Generation Z, which loves the internet. So they really gave us a really strong presence. So, you can visit any of the social media platforms and see, get more information on what we do and how to get involved, and how the organization also supports people starting metabolomics research. So where are we? Where do we want to go? Future projections. Of course, we want to be like all other organizations. We want to be able to host huge conferences, bring together scientists in metabolomics and other related systems biology fields. We do also hope that in the future, the International Metabolomics Society would consider South Africa as a perfect host for the conference. So that is where we want to go. We want to really strengthen and develop the field of metabolomics, especially in the continent. We want to offer you more training workshops. We want to offer you more webinars. We want to make sure you're also confident as you do research in metabolomics. And then we also want to showcase the diverse areas that metabolomics can and is being applied in, so that you too can maybe consider including metabolomics as part of your research. I think I stand between you and hearing more from Microsep and hearing more about LC metabolomics, and more importantly, hearing from Professor Edwin Madala. So I think I will leave it here, and I would of course like to thank Dr. Du Preez for making this webinar a possibility, and also of course the organizers and the organizational structure of Metabolomics South Africa, who are at the moment representing South Africa at the International Metabolomics Society. Dr. Preez, thank you.
Thank you so much, Dr. Sitole. I just want to say that, you know, having some internal knowledge of what MSA does is you guys do an incredible job. These people work very, very hard for this course and to bring the science and metabolomics to South Africa. And they do it all as a community engagement effort. Nobody gets paid for this. It's not a profit organization. People just give their time and give their knowledge and give their ideas for free for the course. And these people really have a passion for what they do. Every time they're in the meeting, you know, people really have this, you can see that they have this strong passion. You don't really get an opportunity to speak because everybody else is always speaking. If you have any questions, please put them in the Q&A session. So Dr. Sitole, I see there's one question from Nelson Mabusela. He says, how do we join journal clubs? I am at TUT doing some research. You're still muted, Dr. Sitole.
Thank you. I shouldn't have mentioned it. I wish Shane was here because he's the best person to answer that question. But you can go on the website or any of the social media platforms and show your interest. And as soon as you sign up to be part of the network, you will then also be included in the emails that go out every week for the journal club ads.
Yes, and there's also a LinkedIn page that was recently introduced. So MSA used to have only Facebook. They now have also LinkedIn recently, and they will post all the opportunities on LinkedIn. As we did for this one. We normally share it also across the different platforms that's here today. Ivan Anderson is saying, thank you for the presentation of Metabolomics SA. I will be glad to join and collaborate. Thank you very much. As you mentioned, there's no joining fee at this moment, so please join so that you can get all the communications and all the opportunities like this one that can be brought to you. Is there any other questions? I don't see any hands. I don't see any questions. I just want to mention that you're also very welcome to refer back to this later on. So if after a different presentation you want to ask maybe Louis or Dr. Sitole something regarding their talks, you're very welcome to also send the questions or ask the questions a bit later. On the point of we love online social media, I really want to encourage you to go and join or like MSA on Facebook, as well as the National Metabolomics platform, DIPLOMICS, and Microsep. Go and like all of these people on, or not these people, these institutions at on LinkedIn, Facebook. Go and check out the websites. You will really get a lot of information there. We're trying to keep up with you younger generations. Okay, thank you so much, Dr. Sitole. I think we will get back to you a bit later with all the closing remarks. Then we're going on to the next talk. We are actually ahead of schedule, so I hope you're all right to start presenting, Bianca. Let me just get your CV there. Bianca Viljoen is a water sales professional for analytical instrumentation. We work together well. As I recall, you're also a student from the Noordwes-Universiteit originally, alumni, as they call it. And we are very proud to see the students become masters in what they do. Bianca's going to give us, sorry, I just lost my paper, a comparison between TQMS and QTOF MS. Thank you very much, Bianca.
Problem. Can you just tell me if you see my screen?
Yes. See.
Okay, perfect. Good morning, everyone. As Ilse mentioned, I'm going to be giving an overview of the difference between triple quad and QTOF, just as an introduction to the application presentation that will be discussed later on. So, what is mass spec? Mass spec is an analytical tool which is used in science to identify and quantify chemical compounds with exceptional precision and sensitivity. It works by ionizing chemical substances and measuring the mass to charge ratio of the ions. Mass spec offers a lot of different key benefits, including high sensitivity to detect trace amounts of substances, which makes it incredibly valuable in applications such as environmental analysis, pharmaceuticals, and in forensics. You get accurate quantification, which provides precise measurements of the concentration of compounds essential, for example, drug development and in clinical diagnostics. You can also determine the structural composition of molecules, which aids in identification of unknown compounds. Mass specs are incredibly versatile and can analyze a wide range of substances across the board, from small molecules to large biomolecules. And then also, modern mass spec solutions offer rapid analysis, which is crucial for time-sensitive applications like clinical testing and food safety. Mass spec's ability to provide detailed molecular information makes it indispensable in both scientific research and in industrial applications. So mass specs are composed of several different key components, each playing a crucial role in identifying and quantifying chemical compounds. First, you have the sample introduction system, which introduces your sample into your ion source. The method of sample introduction affects analysis efficiency and accuracy. So examples include direct injection, GC, and LC. Proper sample introduction is incredibly essential to ensure that the consistent and reproducible ionization is achieved. In LC, for example, it would be best to opt for UPLC systems. Beta chromatography is essential for mass spec because it improves your separation, your sensitivity, and your peak capacity, which then results in more accurate and reliable and reproducible analytical results. Then you have your ion source, which converts your samples your sample molecules into ions. The ionization process is critical because mass spec relies on analyzing charged particles. So different ion sources are used depending on your sample type and your required analysis sensitivity. You also have your mass analyzer, which separates your ion based on the mass to charge ratio. The mass analyzer determines the resolution and the accuracy of your mass spec. So common types include triple quad and QTOF, each with their own advantages in terms of resolution, speed, and mass range. Next, you have your detector. This detects the separated ions and converts this information into measurable signals. The detector sensitivity and dynamic range influence the overall sensitivity and quantification limits of your mass spec. We also have a vacuum system, and this maintains a low pressure environment within the mass spec environment. A high vacuum is essential to prevent collision with air molecules, and this can cause scattering of your ions, which then reduce your resolution of your overall imaging. Lastly, you have a data system, which collects and processes and interprets your data from the detector. A data system includes software and hardware that control your mass spec, acquire data, and perform qualitative and quantitative analysis. Each of these components must function optimally with each other to ensure that the mass spec provides incredibly accurate, precise, and reliable analytical results. So triple quad and QTOF mass specs each have their own distinct features and strengths that make them suitable for different applications in analytical chemistry. Triple quads are highly sensitive and specific instruments, making them ideal for quantifying low abundance compounds in complex matrices. Its ability to do multiple reaction monitoring enables the detection of quantitation of specific analytes with high precision and accuracy, and is particularly useful in targeted analysis. It offers a wide dynamic range, allowing the detection of both high and low concentration of analytes in a single run. Triple quads are incredibly robust and can handle high throughput sample analysis, which makes them very suitable for routine laboratory work. On the other hand, you have QTOF instruments, which provide high mass accuracy and high resolution. It is essential for identifying unknown compounds and elucidating complex molecular structures. They have a wide mass range, which can analyze a broad range of masses, making them suitable to study large biomolecules such as proteins and peptides. QTOFs also offer rapid data analysis, which is beneficial for high throughput screening and real-time analysis. And QTOFs are also very versatile instruments capable of performing both qualitative and limited quantitative analysis. They excel in untargeted application and complex mixture analysis. The triple quad structure consists of 3 quadrupoles. In your first quadrupole, it acts as a mass filter to select ions of a specific mass to charge ratio. Ions produced in the ion source enter Q1, where only ions of a selected mass to charge ratio is allowed to pass through into the next stage. This ion selection process ensures that quadrupole 1 transmits ions of a specific mass to charge ratio to the collision cell, where selected ions are then fragmented. Selected precursor ions collide with an inert CAS, inducing fragmentation through a process known as collision-induced dissociation. These collisions then cause the precursor ions to break into smaller product ions. In quadrupole 3, it acts as another mass filter to select the specific product ions and generated in the collision cell. These product ions are filtered again based on the mass to charge ratio, which allows only ions of a specific mass to charge ratio to reach the detector. The selective process then ensures that only specific fragments of the precursor ions are detected, which provides high specificity in the analysis. Applications where triple quad is best suited is quantitative and targeted analysis, because triple quads are quite ideal for precise quantitation of compounds in complex matrices. They provide accurate and reproducible measurements for analyte concentrations. And the multiple reaction monitoring mode is well suited for targeted analysis, where specific compounds of interest are known and need to be quantified. By monitoring these precursor to product sensitivity, ions, the high sensitivity is achieved, and the instrument enables simultaneous quantitation of multiple analytes in a single run. You can use this in environmental monitoring to quantify environmental pollutants, in drug quantification, to analyze the drug metabolism and quantify drug concentrations, and then also in food safety for specific food contaminants like mycotoxins. Then you have, oh, sorry, I just skipped ahead. Then you have the QTOF, which is consistent of a quadrupole section and a TOF analyzer. The quadrupole section acts as a mass filter, which selects ions of a specific mass to charge ratio, and can also be used as a collision-induced dissociation cell. This flexibility enables the quadrupole to selectively choose ions or allow all the ions to pass through. Once selected, these ions are accelerated into the TOF analyzer, which measures the flight time into the tube. Using known calibration constants, the flight time is then converted into accurate mass charges, yielding high-resolution mass spectra for detailed ion information. Through this process, QTOF instruments achieve high mass accuracy and resolution, which is essential for analyzing complex matrices and identifying unknown compounds. QTOF is best suited for qualitative analysis and applications that require higher res mass spectrometry. They excel in identifying unknown compounds and elucidating complex molecular structures due to the high resolution and accurate mass measurements. This is a vital process for applications that require precise mass determination and fine distinction between closely related molecular species. It can work incredibly well in proteomics, where you need to distinguish between peptides of similar masses to aid in protein identification, and in metabolomics, where you need to identify and quantify metabolites and detect subtle differences between the profiles, and also to determine and identify unknown compounds and characterization of novel substances. This is just a summary of the differences between triple quad and QTOF. Triple quad is best suited for quantitative analysis with high sensitivity and specificity. It performs selected reaction monitoring and multiple reaction monitoring for targeted analysis. QTOF is best suited for qualitative analysis with high resolution and mass accuracy. Each instrument has its own strengths, so choosing between them depends on the specific analytical needs, such as your focus on quantitation or identification, your sample complexity, and the required sensitivity and resolution. So what I did was just to kind of give you a simple guide into choosing between triple quad and QTOF. Now, it's a very complex procedure, but this is a very good starting point to determine whether you need to go triple quad or QTOF. Factors that you need to consider are your sample type and its complexity, your analysis goals, whether you need to choose between sensitivity and resolution. So if your primary needs are quantitative analysis and high sensitivity, your best choice would be triple quad. It offers very high sensitivity for specific low abundance compounds. If you require high resolution and max accuracy, and perhaps have a complex matrix, your best option would be quadruple time of flight. It has high resolution and accurate mass measurements for complex mixtures. That was my very brief overview of the differences, but since we're here for a focused discussion with many metabolomics enthusiasts, my colleague Dylan will be presenting an application on QTOF highlighting its unique advantages, such as ion mobility, which I did intentionally leave out for his expertise. He will be delving into a bit more detail of each aspect of QTOF. Thank you, Ilse.
Wow, that was amazing. I think one of the best overview presentations I've seen. Thank you very much, Bianca. As you said, we have a lot of metabolomics enthusiasts in the audience. I just wanted to mention that we have 137 attendees currently. And, it almost makes me, I don't know, have weird emotions, because I never in my wildest dreams thought that we would have so many interested parties in South Africa who wants to actually learn how to do metabolomics. And I think this is really the reason that all of these parties came together. And this was our aim, is to get the biggest number of people in South Africa to be able to use this technology and really apply this to their research fields. Is there any questions currently for Bianca? As she mentioned, the next talk will go in much more detail. So if you have questions now, then I think you should ask them. If you still have some doubt, if you can understand those basic principles, then you're welcome to answer or ask your questions now. I see there was just a hand up. I was trying to catch the hand, and then the hand was going down again. Anyone? Nobody? Okay. I told you it was a good presentation. They don't have the questions. There's a raised hand. Rose. Rose, I'm going to allow you to speak. You just have to unmute yourself. You have the rights to speak now, and then you can just unmute yourself and ask your question.
Hello.
Hello.
Yes. Can you hear me?
Yes. Yes, we can hear you.
Mine is not a question. I wanted to know whether I'm going to share this slide with us after these presentations.
Yes, we will add this to the different YouTube channels. I just want to get the approval from everybody and the permissions from everybody. But as far as I have it, we are recording the session, and we will share it on the different participants' YouTube channels, and we will send you the link afterwards then.
All right, thanks.
Right. See, I told you, Bianca, it was a good presentation. They already want to share with the other people. We have a comment from Ivan. I hope I'm pronouncing your name correctly, Ivan. It's a very nice spelling. Thank you, Miss Bianca, for your interesting presentation. On slide 4, you talk about quantification and structure elucidation. Which equipment do you recommend between both? Because we can also use QTOF for these purposes.
So Ilse, I'll take that answer, or try and answer that question. If the priority of the analysis or the experiment is first the identification or the elucidation of unknown compounds, unknown metabolites, and that then is followed by some quantitative experiments, then yes, the QTOF would be well suited for these purposes. With QTOF analysis, if your peaks are separated very well, you can do a very good level of semi-quantitative analysis. When it comes to absolute analysis, like determining that there's 5 millimolar amounts of a certain compound in a sample, a triple quad can come into play. There are selected TOFs that have MRM capabilities, but obviously then you would want to limit it to only quantifying one metabolite at a time. So in short, to answer it, I would believe the QTOF would be the correct instrument to go for regarding the question.
Sorry, I was muted. Ivan, if you have, just give us an indication. I guess Ivan says, thank you very much for your answer. We have a question from 𝗬𝗲𝘀𝗀𝗏 Malloy as well. What are the different mass range that you can detect using QTOF and triple quad?
I want to say that that depends on the instrument sensitivity. So I think Dylan has more knowledge on the mass range is specific to each one. But there are different versions of instruments depending on the mass ranges that you require, whether you're looking at low or high concentration, whether you're looking at large or small molecules. Your required application would give us a better indication, like your analysis goals will give it a better indication of what mass range you're working in, and then we would be able to suggest a solution based on that. Is there anything you can add, Dylan? Because it's a very complex answer to give. It's very much dependent on what you require and what systems are available to meet your analytical measurements.
Yes. So yes, 𝗬𝗲𝘀, it is very much dependent on the type of instrument, because as an example, you could have a SYNAPT that has an 8,000 Dalton quadrupole mass range, that instrument is capable of going up to a high mass range of about 8,000 Daltons. You could also have another SYNAPT that was fitted with a different set of mass analyzers and detectors to push it up to about 32,000 Daltons. In terms of small molecule analysis, let's say anything below 4,000 Daltons, typically a quadrupole of 8K or 4,000 Daltons would be more than sufficient. The reason for that is we have to remember that a Dalton mass value is slightly different to what's known as the mass to charge ratio. Yes, we can use the one to get to the other, but as you move up in the mass range, you could have molecules with molecules that are bigger, molecules with multiple charges, and obviously dividing those charges by that molecule's mass, we pull down the mass range to put it back into the quadruple range. For triple quads, I'm not too sure how high the mass range can go, but I do know for QTOFs, you can push the mass range up to about 32,000 Daltons, and in terms of mass to charge ratios, that can go a lot higher.
Thank you. 𝗬𝗲𝘀𝗀𝗏, please, you can, if you need more clarifications, please just add another question there. So we have two other comments in the chat function. So Peter 𝗬𝗲𝘀𝗀𝗏 is asking, can anybody outside of South Africa also join Metabolomics SA? And how can we get info on their website? And Dr. Sitole then replied and said, yes, anybody outside South Africa can also join. The website is www.metabolomicssa.co.za. We will provide, so after this, we will send you a link to the recording, and we will also, in that email where we provide the link, we will give links to all of the different websites and you know, things that we refer to during the day, all the LinkedIn profiles, the Facebooks, all of that. But you can also just Google these names if you are urgently in need to see that. We have a question from Sitandile asking, hi there. Thank you for the presentation. I would like to know about the high resolution that can be achieved in QTOF. You also mentioned that the QTOF offers high mass accuracy. What does that mean? Could you please explain the difference between the two, triple quad versus QTOF? Dylan and Bianca, you're welcome. If you want to read it, that's a long question. You can just look at it's in the chat box.
It is a long question, and it also comes with a long answer. I will try and shorten it, and I think then maybe in the break I will, if possible, then type out a more comprehensive answer to that. But just to give a quick answer to that now, traditionally with triple quadruple instruments, you obtain what's known as nominal mass accuracy. So you can think of, as an example, a caffeine molecule that has a mass of 195, just the integer mass. If you run that same sample, that caffeine sample, on something like a QTOF instrument, you would obtain what's known as accurate mass, where you have decimals, the monoisotopic decimal masses that contribute from each element within that compound. And based on these decimals, these accurate mass values, you are able to derive a very accurate, well, depending on the type of instrument, QTOF instrument used, you're able to derive a chemical formula that you can use to identify the molecule that you are trying to analyze if it's an unknown molecule. So the better your mass accuracy is in terms of a QTOF, the more sensitive and more selective you can be about generating chemical formulas, and how, I was going to say how easier, it becomes simpler to determine or structurally elucidate certain unknown molecules. Resolution kind of goes hand in hand with mass accuracy. Depending on who you ask, there are different definitions of resolution, whether it's chromatographic or mass spectral resolution. But in terms of mass spectrometry, it's the ability of the mass spec to distinguish between two masses. Obviously, from a nominal mass side, the triple quad side, it's the ability to distinguish a mass of 195 to 196. From a QTOF side, it could be more specific, looking at those decimals, being able to separate 195.001 versus 195.002. That's a bit of an ability of QTOF's mass accuracy, resolution, my apologies.
Thank you. So as Dylan said, yeah, it's difficult, but Dylan is one of the best teachers I've ever had. He explains very well. We will try and type it out in the break. Then there's a question there. Thank you, Dylan, from 𝗬𝗲𝘀𝗻𝗲 from Ethiopia. So amazing. Thank you for joining all the way from Ethiopia. The question is, what other requirements are needed for LC-MS triple quad to be used for targeted metabolomics? Thank you.
Yeah, I kind of want to ask to expand on that question.
It is a very broad question.
Yes, because essentially for targeted metabolomics, you would need to know what you want to achieve from this. What are your target analytes within your sample that you're looking at? And an idea of whether you're looking at low concentration analytes or whether it is suitable for medium sensitivity. So that would also determine the sensitivity of the instrument that we would be looking at. Triple quad is ideally used for targeted analysis. So it depends on what you want to see and whether you know that those compounds are in your mixture.
So if I can just answer from a diagnostic perspective, and I don't know if this was the question. So apart from the instrument, you need you need to know, as Bianca said, which analytes you're looking for. You need standard compounds for those analytes. So to know that you're seeing what you want to see phenylalanine, you need pure phenylalanine as a standard to make sure that you're seeing what you want to see. You also need calibration curves if you want to do absolute quantification for purposes like therapeutic drug monitoring and diagnostics. You also would need quality control samples that you can buy from an external party that you can, in this quality control samples, they will tell you that it should be a concentration of 5.23 nanograms per whatever, and then you need to also be able to quantify to that exact number. So if it's targeted in terms of absolute quantification, absolute validation of a method, then those are the other things that you would require. And then obviously you need an expert in the instrument to help you to set that up. So 𝗬𝗫𝗍, if you have more questions, I'm not sure if we answered you correctly, please continue with that question. I thought we were making up time, but we have so many questions. I'm going to allow more questions because the next round is supposed to start at 11:15. So I'm just going to give more time for questions if that's okay, Bianca.
Yeah, not a problem.
Okay, so Nelson Mabusela is asking, does it require concentration adjustments or standardization, mainly from different sample extracts? Nelson, I don't know if you want me to unmute you because I think this is a bit of a broad question.
Yeah.
I'm not sure what you mean with concentration adjustments, but we do use internal standards as a means to adjust for variations in instrument drifting and sample preparation. And as I just mentioned, you need to use calibrators for different sample matrices that's in those sample matrices specifically. So if you're using urine, you need calibrators in urine. But Nelson, please continue the chat or just put up your hand and I can unmute you if you wanted to elaborate on that question. Just see if there's some hands up. There's a hand up. So Nelson is, there you go, Nelson, you're allowed to speak.
Oh yeah, thank you for the wonderful presentation. So yeah, I needed to check in terms of concentration ranges, but I think when you spoke about the instrument drifting and the preparation and quality control of particles, it may have actually touched on what I wanted to check. Because for example, I have different samples using different solvents, and I needed to check that if one was to actually explore that, would it then require maybe preparation from the lowest concentration, and what would that be into the highest concentration, and what would the most highest concentration it could take if there's possibly a spec and those kind of things. But I think to a particular extent you may have touched on it, but if you have more detailed answer, you can then deliberate on it. Thank you.
Sorry, when you validate the method, you also do certain specific tests to determine your analytical range. Your analytical range is what you can measure comfortably with the correct accuracy and precision to measure in that specific range. So you need to, before you set up your method, you need to know what we call it the medical range. If it's not in a medical setting, you need to know what is the range that you want to detect very well. And then you need to work in that range. You remember, if the concentrations are too high and it falls beyond your analytical range, you can always dilute your sample, or you can inject less. So if you normally inject 10 milliliters or microliters, you can inject 1 microliter or whatever. So you need to set up your sample preparation in a way to match your analytical range as well, if that makes sense. So we have a lot of methods where we dilute the samples beforehand just to get it into that analytical range and measure it accurately instead of injecting a highly concentrated sample. The questions are coming in, guys. From Palisa saying, good morning, thank you for the presentation. It's a pleasure. On your behalf, Bianca, it's a pleasure. Then there's Moipone Lebeluane. Morning, great presentation. Please explain the Q1, Q2, Q3, and triple quad in simplified terms. What informs the selection of the ionization source? There you go, Bianca. It's all yours.
these questions are a bit complex, hey? I thought I tried to keep it as simple as possible.
Yeah, I think they want to just
yeah.
understand what is the Q, the quad,
Yeah.
what is that, and why do you have 3 of those?
So,
We
so
actually
as I
have
mentioned, yeah, so as I mentioned, there's 3 quadrupoles in a triple quad. The first and third quadrupole acts as mass filters essentially. So you select a specific mass to charge ratio that you want to analyze, and quadrupole 1 and quadrupole 3 filters those masses. Quadrupole 2 is a collision cell where your product, your precursor ion, which you selected in your quadrupole 1, is fragmented and then selected in your quadrupole 3. Those fragments are your product ions, which you then detect. What informs the selection of the ionization source?
I'm actually also not very sure about that question. At least to bring in the source question into mind, during your analysis, your sample analysis, the ion source isn't very selective towards the molecules you want to analyze. It converts every molecule you're analyzing from the liquid to the gas phase if you're using chromatography as the front end, and then it goes about ionizing the molecules, well, all the possible molecules in your sample. All those molecules then move to the first quadrupole, and that is where that quadrupole filters out everything else, only selectively keeping or allowing the mass, the molecule that you want to analyze through the quadrupole, the first quadrupole.
That's why, because you actually choosing your mass range and you selectively looking at those ionized compounds, that's why it's well suited for targeted analysis, because you know what you want to see. You just want to see if it's there, and you're choosing the mass range of what you want to see. That's what you use the quadrupoles for. And I hope that's simpler.
Yeah, so if you want to see a product ion of 50, then you can set your quadrupoles to only let a mass of 50 go through. And you can see them, you can determine the masses that you want to go through from your compounds based on literature or based on prior experiments where you optimize your samples and try to find the MRM. And this is what 𝗬𝗫 is now saying here is, so the previous answer was, what are the other requirements that you need for targeted? And the follow-up is saying, thank you. Our samples are food and biological samples, and I'm just trying to raise issues like MRMs and sample spraying accessories. So maybe you can explain MRM, which will then touch on what triple quad is and why you need triple quad. So what is the MRM, maybe in very simple words? Thank you, Dylan.
In simple terms, MRM is multiple reaction monitoring. So you select a specific mass range in your first quadrupole. That is your precursor ion corresponding to your specific metabolites of interest based on their mass to charge ratio. So you can select either one mass range, or you can select a multiple, or you can either select one mass, or you can select a multiple range of masses. So for example, between 50 and 200. Then it would go through to the collision cell where it's fragmented, and this fragmentation process then produces your product ions, which is then used to quantify your product ions after detection. So
if I can,
I'm trying to overcomplicate it now, Dylan. Please, if you can maybe,
So in your 3 quadrupoles, the first quadrupole is there to filter or select for the one molecule of interest that you want to quantify.
Or molecules.
Okay. But because it's a nominal mass instrument, obviously you could have multiple molecules that still have the same integer mass. So that's not specific enough or selective enough for quantification yet. So we divert that one molecule from the first quadrupole to our collision cell, where we fragment it. and then we select a very unique, or what's known as a qualitative ion of one of those fragments, and only that qualitative ion is allowed to be filtered or pass through the third quadrupole and then strike the detector to get detected. So typically yes, with MRM, it's what's referred to as one parent, one fragment. But for quantification experiments, we would typically have, yes, still one parent, but one qualifier ion to ensure that, yes, the molecule that we are quantifying is indeed the one we believe it to be. And then also a quantifier ion, which would typically a lot of the time be the most intense fragment peak in your spectra. And that the intensity of that fragment would be used for quantification purposes.
Okay, so in other terms, you have a molecule that's a ball. You detect the entire ball in Q1, okay? So if you say this ball weighs 50, then you see the entire 50 in the first round. Then what happens is you blow it up, you chop it up into different smaller pieces, and then the way that it chops up is unique to a compound.
Yeah.
So what you can do is you can say, if I see the parent 50, you will have a lot of 50s, okay? Because there's a lot of people weighing 50. But if you chop them up, and then you look for a specific fragment or a specific, little smaller piece of that person. So I'm saying person, it sounds a bit weird, but if you chopping up the chocolate and you get the little small piece, so then you can match the bigger one to the smaller one. And that match is unique to a compound. Not always super unique, but in the run that you do for the 10 compounds that you're looking for, it will be unique between the 10. So if you say, I'm looking for a 50 and I'm looking for a 25. And if you find a 50 and a 25, you can most probably, with a lot of accuracy say, this is the compound that I'm looking for. Okay, so it's basically a puzzle that you have initially, and then you break up the puzzle, and then you detect some puzzle pieces at the end, and then you can identify. So in basic terms, for someone who has never ever done this before, I think that might help.
It's a very crude way of explaining it, but for the way I'm going to explain it now, because it might be a bit bad, but I like using it because it helps, because you can visualize it. It's like saying Ilse, Dylan, and myself were going through to Q1. We all weigh the same, so we're all going to be detected. But my arm, Ilse's arm and Dylan's arm, have different masses. So when we go through the collision cell, my arm is cut off. It weighs different than Ilse's. It weighs different than Dylan's, but you only want to see my arm at the end. And the third quadrupole detects my arm's weight. So it's the same thing broken up, and then that fragmented compound has different characterization, even though it's the same mass that went through. If that visualizes it a bit in a crude way, but a bit better.
Yeah, I think that helps. Thank you. So we have the last question I'm going to take for now, and then we can continue to the next session, is from Amber, asking, good day. Thank you, Bianca, for a great presentation. I'm going to be running metabolomics and profiling of a drought-stressed crop with unknown drought metabolites in literature as well. Between quadrupole and QTOF, which one of these two would best suit my profiling of these metabolites?
I would definitely advise a high-resolution instrument that's capable of generating accurate mass, which would be the QTOF instrument.
Yeah, because you're looking at, you specifically mentioned unknown. QTOF would be best suited for unknown applications.
Yes, I agree. You normally use QTOF when you don't know what you're looking for.
Yes.
And then you're using triple quad when you know what you're looking for.
That's it.
Okay,
yes.
I think we should go on to the next session. Thank you, Bianca. If you can give a presentation and have a longer questions session than your actual presentation, it means that you really intrigue people. So thank you very much for that.
It's a
And
pleasure, Ilse.
thank you for the great participation from the audience. If you have more questions, please post them now. We're just going to move on to the next session so that we don't run out of time, and then we can get back to the other questions. So if you thought that that led to a lot of questions, the next session from Dr. Dylan Zeiss is gonna have much more questions at the end, or maybe none, but I guess we'll have much more questions. Let me just get to your thing here. So Dr. Dylan Zeiss is a waters application specialist. He's an expert in QTOF MS applications, leverages his extensive knowledge to provide exceptional support and solutions in his role as a waters application specialist. I know that you did your PhD at UJ in metabolomics, working on a waters instrument. And this is just my humble opinion, but Dylan is definitely one of the, or perhaps the best expert in this technology that you will meet in South Africa. So you are very privileged to have someone like this giving you this training. Thank you so much, Dylan, for giving us your time and for all the time you took to prepare this. We are looking forward to your presentation. Thank you.
Thank you, Ilse. I trust everybody can hear me, and I trust everybody can see my slide.
Yes, everything perfect. Thank you.
I also don't believe I'm the best in South Africa. I think there's lots of room to improve, but thank you for the compliment. All right, good morning, everyone. My name is Dylan Zeiss. As said before, I'm the MS Application Specialist at the Waters Division of Microsep, and today I'll be giving a talk on the untargeted metabolomics workflow and what factors should be considered when performing this type of analysis to enhance our data quality as the researcher and enhance our overall data output. So this is a general outline of the talk that I'll be giving, detailing the various topics and aspects that we'll be discussing. So we'll start with just discussing the goals and challenges of metabolomics and what we as the researchers can do to more tightly control the workflow to increase our overall metabolite coverage. From there, we'll have a look at the general funnel or the untargeted metabolomics workflow, as well as what's known as the funnels in each of the steps of the workflow. And then obviously, as part of that, we'll also delve into what we as the scientists can do to minimize the analytical variance within our analysis to enhance our overall data quality in order to see the clearer and bigger biological picture. In some sections of my presentation, I will be discussing some LC-MS concepts, and I will be using the following instrument on the right, a QTI class coupled to a SYNAPT G2SI instrument, just using it as a case example. If you do have any questions, I would invite you guys just to take note of the little numbering system in the bottom right-hand corner if we have to then navigate to a specific slide which you have a question around. So we know that the metabolome of each organism holds a complete and incredibly diverse set of metabolites, with our compounds varying widely according to their physicochemical properties. And these physicochemical properties can range from molecular weight, polarity, their conjugation, as well as their overall cellular abundance or cellular concentration, as well as the localization where you would find certain metabolites in organelles of certain biological systems. And because of this wide diversity or these wide physicochemical properties, it makes it extremely challenging to develop a one-size-fits-all analytical methodology that allows us to identify and screen and measure all these metabolites. So why do we do it? Well, the metabolome has been shown to be closely linked to a biological organism's phenotype. And due to the dynamic nature, changes that the organism experiences due to environmental conditions, due to physiological or disease states, these effects have a direct reflection and have a direct impact on total metabolism, which makes studying metabolomics very attractive when it comes to biomarker discovery or better understanding the interconnections between metabolic pathways. However, something that I would want to touch on, in recent publications from leaders in the field of metabolomics, they have revealed that there are frequently errors in submitted works at various stages of the untargeted workflow. Yes, metabolomics is very data rich, and as a result, it is very attractive to study it. But as a result of it being so complex, mistakes do happen. And these mistakes can happen during the pre-analytical steps, during LC-MS analysis, data treatment and statistics, during the identification stage, or just simply translating the information back to the biochemical aspects of the research. But due to this complexity in metabolomics, poorly conducted studies can undermine, what was the other word, or result in a loss of confidence in the value that metabolomics and metabolic profiling can provide in research and discovery work. And what's worse is that when literature or articles, research is published and critical information, missing information, or just critical steps were skipped in the workflow, this can lead to erroneous results. And what's worse is it can lead to erroneous hypothesis, future research being based upon those incorrect results. So really, what do we want to do? What is the total goal in metabolomics? We want to control the total experimental variance that we have so that we can maximize the biological variance or the biological phenomena that we are able to observe. Let's have a look at the untargeted metabolomics workflow. So this is just a very quick schematic of showing the workflow. We can make it a lot simpler. We can make it a lot more complex as we move throughout the steps. Traditionally, it does start with an experimental design, which just gives you a blueprint layout of each of the steps that should be followed. We would then identify the type of biological organism that we want to study and proceed with sample collection. Once the sample has been collected, we need to perform some level of sample preparation to get our biological system that we want to study in a format suitable for analytical analysis. Frequently, in terms of untargeted metabolomics experiments, LC-MS is the favored or one of the favorite analytical systems that get used. During the chromatographic step, all our molecules in our sample extract are separated according to various chemical properties that we as the researchers can control. This could be due to polarity, charge state, or size, just to name a few. And following our chromatographic separation, our molecules can also then be detected through mass spectrometry, high resolution mass spectrometry. And really, it's at this point, before we jump to data mining now, that I would like to kind of put a pause or take a small breath in the workflow. I like to call it a save button. We can click save, that we've done the first few steps now, and that we can look back and assess each of the 4 steps to ensure that we have done, that each of those steps were performed as adequately and as correctly as possible. And the reason we also have this break is once the data has been acquired and acquired correctly, our data mining or pre-treatment, our data processing, our statistical analysis, and our annotation can be performed and re-performed. Once the data is there and the data is correct, it can be mined and remined. So any errors that we make from the halfway point forward can be corrected by just redoing or remining the type of data. And then from there, yes, we would take our raw mass spectral data, we would convert it in a format that is suitable for us to perform statistical analysis, obviously with the sheer number of metabolites that you have in one sample, ranging from hundreds to thousands, and then scaling that up to having 200, 300 samples, determining which molecules are deemed statistically significant in those samples can be a bit of a task, a bit of a challenge. But nevertheless, we perform our statistical analysis in order to determine which molecules are deemed statistically relevant. And for those molecules, we would selectively focus to identify them first or annotate them first because they show the greatest positive correlation or perhaps a negative correlation towards the biological question we are trying to answer. Finally, we want to link all the biochemical information, and we want to report our findings. With reporting our findings, we want to make sure that each step is described as detailed as possible, so that information is not lost, because it frequently does make it hard for other laboratories abroad to replicate our findings when there is a lot of missing information in terms of the sample prep, the chromatography, the mass spec, or the processing. But really, the take-home message of this talk that I would like to emphasize is that for each one of these steps, there should always be some sort of check or validation step, or sometimes multiple validation steps, to ensure that each step in the untargeted workflow is performed as optimally and as correctly as possible. So this is the metabolomics workflow, but it can be viewed from a different way, in a different light. Because the field of metabolomics is still maturing, as Dr. Sitole mentioned at the start, we often encounter what's referred to as funnels in the metabolomics workflow. This simply means that with each step, there are constraints or limitations at each step of the process, and they limit the total amount of biological information that we are capable of observing. And as you move through each of the funnels, there is data loss, biological data loss that we experience. And only by us implementing checks or validation steps, we are able to maximize or minimize the overall data loss in each of the steps and maximize the total amount of information, the biological snapshot, the picture that we're able to perceive. In some cases, it is very hard to eliminate the analytical variance. In those cases, the one example I'll give now is in sample prep. It is then important to be very well aware or have that analytical variance well characterized so that you can assess if it is having a significant effect on the biology that we are seeing. So having a look at this workflow map, we can see from the study design already, before we even move into the biology or the laboratory work, we would have several limitations in terms of the overall chemical diversity of the metabolites that we're analyzing, the cellular concentrations that those metabolites might be in. Frequently, when it's in vivo, when it isn't a biological organism, metabolites can experience what's known as biotransformations. These are various modifications that either enzymatic or non-enzymatic can be made onto these molecules, which can impede the total answer we're looking at. Subcellular localizations and environmental susceptibility were ones that we discussed. When we get to sample prep, it's a bit of a catch-22. We try and be non-biased in the way we extract our metabolites that we want to analyze. But the bit of a challenge or the hiccup with this is just by the solvents that we are using in our extraction method, we are already creating a bias inherent to certain molecules. Because obviously during LC-MS analysis, we want to use solvents that are compatible with the instrument, the analytical system that we want to use. Regarding LC-MS separation and detection, the technology and the instrumentation will always inherently have some sort of limitations in terms of what can be seen, how fast things can run, overall dynamic range, what can be ionized. But science is always advancing, and these funnels are slowly getting smaller. I do believe probably the greatest challenge in the metabolomics workflow would be the data processing step, and specifically metabolite identification, where misidentifications can wreak havoc, and that is where we draw false conclusions. Finally, linking everything to a biological question. So let's start at the first step of the experimental of the workflow, which is experimental design. And very crucially, this is a step that is often neglected and really should be taken seriously, should be taken into account. So experimental design is defined as designing a study to acquire data related to a biological question we have. And while we as scientists are trying to answer this, during our process, we should be eliminating any external variation, eliminating or removing external variation, or at least ensuring that it is well defined or well characterized. In very simple terms, your experimental design is a blueprint that we can use to construct the roadmap of each step in the workflow to ensure that our final product, our data, our results are correct at the end. And our experimental design is there to provide a statistically robust investigation from which we can draw scientifically backed conclusions. And a bit of a hiccup that I have noticed in science is whether the study is hypothesis testing, testing a hypothesis, or hypothesis generating, the analytical variation inherent in the experiment should be controlled. And this is frequently neglected when it comes to the hypothesis generating experiments such as untargeted metabolomics workflows. So this is a figure that I just scrambled together, which I believe every researcher should draw up during the experimental design so that we can note which control measures we put in place to assess and monitor the accuracy and correctness of each step in the process. And then again, to monitor how we successfully completed them. These checks are there to notify us as well at which point in the workflow something might have gone wrong, and they also provide us a bit of information on how we're then able to correct it. So without these checks, we have no way of assessing the quality of the data we're working with, and we draw incorrect conclusions from incorrect data. Just touching on a few of them briefly. Having background knowledge on your biological system is paramount. Having a standard operating procedure for sampling and storage is crucial, and obviously being consistent throughout works. During your extraction step, having biological and technical replicates is always useful. The addition of internal standards, pulling together quality controls, randomizing your samples, and using high quality consumables. For LC-MS analysis, we always want to make sure our instruments are calibrated. We can run an SST to verify that our instrument is working correctly. And obviously, for more high resolution instruments where mass accuracy is the name of the game, monitoring things like your lock mass becomes important. Having blanks or no injections, always useful to monitor the steps. Data processing, we can have a talk about that a bit later on. And then obviously with our standard annotation, being able to methodically go through the process of annotating metabolite and having the information that you can report with confidence is paramount. So going into sample preparation, I won't touch too long on this. The purpose of your sample preparation is to get your sample in a format where the metabolites in that organism can be measured using our analytical technique. An ideal sample preparation should be carefully considered, especially if the metabolic contents are unknown. An ideal sample prep method should be unselective, simple and rapid with the minimum number of steps required. It should be reproducible. Controversially, it should include a quenching step to stop the metabolism, stop enzymatic reactions, things like that from occurring. And obviously, it should be low variance. So from a controversial step of the quenching step, yes, we always need something to stop the biology so that we can see this biological snapshot in time. But oftentimes the type of quenching that is applied can inadvertently change the metabolism, and you see a bit of a skewed picture of it. Nevertheless, and then finally, in sample preparation, sample prep, solvent quality in which the samples are resuspended is important. It's crazy important. At minimum, from my side, I would recommend that the samples are always resuspended in MS grade solvent. I'll touch on why. That the sample should be filtered through a 0.22 micron filter to prevent any potential blockages in the flow path. and then possibly diluting it. You can always work backwards, inject the sample, see it's a bit too dilute, you can't see a lot of peaks, and then work backwards. Some very good ideas that can also be added during the sample preparation step is the addition of an internal standard to the initial extraction solvent to assess your metabolite losses during extraction and handling. And a very good benefit of adding an internal standard is it provides you with very persuasive evidence when it comes to data reporting that the cellular metabolite composition that you are seeing is a valid reflection of what is really happening in the biology. In addition, it can also be used, an internal standard can also be used to monitor the extraction efficiency between samples and between batches. Finally, creating biological and technical replicates normalizes the biological variance and can help us to reveal biological outliers. Creating a pooled QC can assist us with instrument monitoring and equilibration prior to analysis. Moving into probably the most critical step in the workflow is chromatographic separation. And here, solvent quality is the most critical thing ever in untargeted metabolomics analysis. I have had numerous headaches on this topic. Wherever possible, LC-MS grade mobile phase should be used when performing the analysis, especially on a high resolution instrument. And this is because the solvent should be fit for purpose. What do I mean by that? Yes, compared to LC or AR grade solvents, LC-MS grade does have a higher purity due to lower level contaminants, but it's not just about the contamination levels, it's also about the additives. The second reason is the solvent additives. So during manufacturing, vendors would create their solvents and obviously store them in a warehouse until they're sold. And during that storage period, the vendors add additives into the solvents to ensure that they remain stable and remain pure over prolonged times. But this becomes a bit of an issue when you're running something like LC grade solvents on a high resolution MS, because the additives that are added onto in an LC grade solvent are not the same as that of LC-MS grade. The reason for that is the detectors that are used. For LC experiments, typically it's an optical detector like a UV or PDA, and those additives that are added in LC grade solvents are not seen by those detectors. But the moment you use LC grade solvent on a mass spectrum or high resolution mass spectrometer, those additives are seen, and this contributes to an increase in the baseline noise. Just to illustrate with this nice animation, what you can get a lot of the times when you use LC grade solvents with a high resolution instrument, well, the first one is you can have peak shifting, you can have a very high baseline noise. The final thing that I might have skipped over is with LC-MS grade solvents, I would advise, when possible, purchasing one that has been pre-filtered. A lot of the times, if you attempt to filter it on your own, you'll find your filters are more contaminated than the solvents that are nice and pure. But when we use LC-MS grade solvents, what can we obtain from that? What does it give us as the researchers? Well, it gives us a decreased baseline noise. That's one. Enhanced instrument performance, a reduced risk of contamination, lower baseline noise, and this helps us to identify new molecules that might be in very low abundance in our samples. So it increases the sensitivity and detection limits that we're capable of. And it also then helps us to determine which molecules might be contaminants, background contaminants, ghost peaks, things like that. Next, in the separation step is the choice of the analytical column that we should be using. I won't spend too long on this. In my very biased opinion, I think you need 4 good columns to unlock an entire metabolome of an organism. And something to note is that separation is not just governed by the ligand that's attached to the stationary phase. Yes, we all talk about, we use C18 columns, but it's not just about the C18, the ligand. A lot of the selectivity is also attributed to the base particles that are used, as well as the surface coating on these particles that give us additional selectivity for metabolite separation. So the 4 columns I could choose, HSST3 for more polar to mid-polar range molecules, BH, which is a hybrid particle technology for general purpose, It works very well for metabolomics types experiments. CSH columns works very well for medium to very non-polar metabolites, such as lipidomics type experiments. And then finally, as part of the BEH technology, you can also have what's known as HiLEC technology, where you focus on heavily polar molecules that might be in your sample. As an additional step to mitigate carryover between samples, the next generation of Waters columns also have what's known as this high performance surface, this purple coating on the inner lining of the column. And the benefit of this is that you prevent metabolites from sticking onto the internal walls of the column. You prevent carryover. So in terms of the checks that we mentioned through each step, having a column like this already allows you to take the idea of carryover, at least from your column, off the list. And then just quickly to demonstrate how having two different columns, using two different columns, can produce very different results. This was an experiment performed by this research group here, where they, I believe it was serum, they analyzed serum in different positive and negative ionization modes using two different columns, a reverse phase column and then a HiLEC column. And we can see from this Venn diagram that through each experiment, they obtained very unique molecules for each specific analysis, and the total overlap was quite minuscule. Now, yes, this is a very drastic example, but it illustrates the point. The largest development in high-throughput metabolomics was and still is the advancement of UPLC technology. Chromatic graphic separation is often overlooked when coupled with high-resolution MS systems, and the speed and the total time of analysis is typically dictated by the slower of the two analytical techniques. Where chromatography operates on a minute to second time scale, the mass spectrometer operates on a millisecond to microsecond time scale. And the difference between this results in the outcome being dictated by the slower system, which is the chromatographic system. However, we can use this to our advantage, where minor improvements or optimizations in the LC dimension can have dramatic enhancements in the quality of our mass spectral data, especially when it comes to fragment ions, which are essential for accurate metabolite identification. Effective separation and resolution of complex metabolite mixtures improves the overall downstream analysis. From an MS standpoint, we would obtain spectra that are less convoluted, or they are more deconvoluted, and it allows us to easier match fragments back to the molecular ions. Having robust chromatography with good peak shape also has a positive impact on downstream statistical analysis, which makes it easier and clearer for us to then calculate candidate biomarkers. As the old saying goes, good chromatography can make great mass spectrometry, but great mass spectrometry cannot fix bad chromatography. And then as a final thing, to monitor the overall instrument health and performance, which is often overlooked, how would we perform this? With the addition of what's known as a SST, a system suitability test, or at least a reference material. Very simply, this is a sample vial with compounds dissolved, with various compounds dissolved in it. These compounds were carefully chosen because they ionize in both ESI positive and negative mode. They cover wide mass range, and they can be separated under various chromatographic conditions. So what instrument operators typically do is they would inject this SST before running their biological systems to ensure that, yes, the instrument is running at its peak capacity, it is running correctly. And they can make this assessment based on looking at retention time stability, the column health, mass accuracy, and the baseline noise. And I would take this one step further by saying that even if you might not be an instrument operator, if you might be sending your samples to be run on an instrument, that you should perhaps be adding or requesting that an SST or reference material be injected as part of your sample list setup, in order for you to have that confidence, well, from both sides, the operator and the researcher side, for you to have that confidence to know that the LC-MS system was working as it should. Obviously, then when we set up our sample lists, we should add multiple pooled QC injections at the start of the run. This helps equilibrate the system and produces a reproducible signal response. To remove systematic error, we should randomize our samples before running, optionally adding in technical and biological replicates so that we can monitor for outliers. And then obviously adding in a QC sample after every 10 or 20 injections to monitor the batch effect or the instrument drift. In this regard, I would also then suggest using the SST. And then to further establish or improve chromatographic separation, I would advise that we as researchers look at the LC method that we use. With a chromatographic method, yes, we have these 4 steps: our initial hold, our gradient separation, our final hold, and then our re-equilibration step. And they are there set with specific purpose to re-equilibrate the column, to ensure that we elute more polar junk that might be on the column, to elute more non-polar molecules that might be on our column. But something that is often missed is how long these these sections should be specified. And here I just provide a very brief and basic outline of what should be monitored. Obviously, these can be optimized as necessary. Other tunable parameters from a chromatographic perspective would include flow rate, either increasing or decreasing it, using pH to change the protonation or deprotonation states of molecules, specifically so that we can achieve better separation, the use of organic modifiers, and the use of column temperature or selectivity attributes has very high implications and can add a lot of selectivity in your run. Additionally, one extra thing that I believe is unique towards this technology is during our gradient separation step, we are able to change the slope of the gradient. We can change it to step, slope, convex, concave, and the benefit that this has is we can avoid or minimize some of the dead volume between peaks while we're waiting for the elution to speed up our overall analysis. From the mass spectral side of things, the first section in our mass spec is our ion source, which has 2 critical functions. The first function is the phase conversion, converting our samples which are in a liquid phase that was separated by chromatography into a gas phase. And then the second function is to ionize our molecules so that they can be viewed or observed by the mass spec. Obviously, if a molecule is not ionized, it cannot be seen by the mass spec because we are unable to control or manipulate the movement through these of these ions through the mass spec using electric or magnetic fields. So in the cases where we have ions that or molecules that don't ionize well, what do we have? Well, we have a lot of different ionization modes that can be used. Electrospray ionization is a very popular technique when it comes to metabolomics analysis, but selected molecules just don't ionize well. And if they're absent in the data, we believe they're not there and we are missing biological information. In that regard, an alternative ionization method I could suggest is what's known as APCI, atmospheric pressure chemical ionization, which can bridge this gap. It offers a different mechanism of ionization compared to ESI, where ESI molecules are ionized in the liquid phase and then drift into the mass spec as they desorb. With APCI, the molecules are first evaporated, and once in the gas phase, they are then charged. APCI is what's known as a harder ionization technique, and it tends to produce more fragments than ESI, but it is compatible with higher flow rates, analyzing more dirty samples. So the idea of ion suppression is less impactful with APCI. And then finally, the addition of modifiers into the mobile phase to always improve ionization efficiency and overall selectivity, such as formic acid, ammonium formate. There are several benefits and drawbacks to this. Using formic acid, obviously, we might inadvertently drop the pH down, leading to the protonation of certain molecules where they then cannot be ionized and we therefore cannot see them. When we then move on and we want to analyze the metabolites, we record them or measure them based on what's known as their mass to charge ratio. For untargeted experiments, this can start with a full scan and then quickly separate off to one or two strategies that can be employed. So that would be either data-dependent analysis or data-independent analysis. I would just also like to quickly remind you guys for the future, I added a pin here, which I will come back to in a few slides. So starting with traditional data-dependent analysis, in this mode, the MS instrument switches from a full scan MS mode to MS-MS mode when a co-eluting peak that we have selected, we as the researchers have selected, rises above a certain intensity threshold. The precursor ion or ions that are under that peak are then specifically filtered by the quadrupoles and selected for MS-MS analysis. This results in the fragmentation of solely the peaks or the mass spectral peaks or mass spectral precursors that are under that chromatographic peak. In very simple terms, we're telling the mass spec which peak we want MS-MS information on. And for these type of analyses, you do need prior MS information about your samples or your peaks that you want to analyze, something like a full scan. If it is a completely untargeted or completely unknown type of analysis, I'm not quite sure how well DDA fares in that regard. So let's have a look at what happens when we fragment this molecule. In this mode, we can see all the precursor ions, and again, we as users can select the number of precursors that we would choose to fragment. So in this case, we selected the top 5 out of the top 7. And kind of by doing this, we set the overall dynamic range of the metabolites that might be sampled, in this case to the top 5 most intense peaks. But this number can be set during the analysis. We then perform MS-MS fragmentation on these and we get our results. With DDA types experiments, however, there is this natural bias towards certain types of metabolites where we focus on the more abundant ions and we are potentially missing out on the less or low abundant ions. Another drawback of DDA methodologies is that there are limited time for fragmentations. Chromatograms that are acquired during DDA cannot be used for quantification because often while the mass spectrometer is busy collecting MS-MS data on these ions, they are still continually eluting off the column, and getting an accurate quantitative extracted ion chromatogram becomes difficult. Often the apex of your peak is missed and you frequently don't have enough data points across the peak for good quantification. This can be mitigated by dynamic exclusion, but it still remains biased to a certain extent. DDA does have the benefit of being more selective and specific on the fragments that you acquire on the precursors. And if you would like to learn more about setting up or optimizing a DDA method that you have, I would highly recommend this article, which outlines the optimization strategies. One of the co-authors is a Waters colleague, and it is a good read. Next, we have a more modern, what's known as data-independent acquisition. In this case, at Waters, we call it what's known as MS to the E. During DIA analysis, the identities of possible metabolites in our samples are not known, and there is no pre-selection made from our part on which peaks we want to focus on. Everything gets treated equally, everything experiences the same mass spectral conditions as the other. So to avoid the loss of any spectral information, the precursors and the fragment ion information is acquired on every detectable sample or every detectable component within every sample. Again, this is what Waters describes as MS to the E. And looking at this diagram, this is achieved by alternating between low and high energy conditions. While the QTOF is scanning, this happens in the collision cells. We end up getting precursor MS and fragment ion information. And by obtaining the maximum information, we eliminate the need for a second or third analysis. Even if the spectrum is convoluted with fragments of different components, we are still able to assign the fragment ions as we can see here with the blue, to their original precursor molecules. And that is due to the chromatographic link. This is what separates MS to the E analysis from traditional collision ramping experiments, that retention time link stays valid between the precursors and fragment ions and allows you to deconvolute the spectrum. And with DIA strategies, it facilitates identification as well as quantification, even if it's just semi-quantitative analysis, quantitative workflows. I would, from my side, highly recommend or highly advise MS to the E, or at least a DIA approach when performing untargeted metabolomics experiments. But irrespective of the type of MS analysis that we're doing and what we're using to acquire our sample data, mass accuracy is key. Mass accuracy is the name of the game. I've said it twice now. And it ensures that our downstream analysis is correct so that we can get precise identifications of molecules, either by matching the experimental mass to a chemical formula, as shown here, by matching our mass to a chemical formula, or by matching it to a theoretical database or library. The general consensus in science at the moment, I believe, is that a mass accuracy below 5 ppm is sufficient for a positive identification as a first step. But with more modern instruments like the SYNAPT, we can push the boundaries of that mass accuracy to 1 ppm and even sub ppm levels. The caveat is that due to small changes, fluctuations in the power supply, cleanliness, our laboratory conditions, we can experience a shift in our instrument's ability to report good, accurate mass. And simply put, when we have a deviation between the theoretical and the experimental mass, we can't get a correct answer when it comes to annotation. So how do we monitor and correct our mass accuracy during sample batches? Well, we infuse what's known as a lock mass. A lock mass, very scientifically defined, is a contaminant that we know of that is introduced as a standard into the ion source together with our sample that is analyzed, and it permits a real-time recalibration or correction of any mass spectral shifts that might be arising due to instrumental drifts. For most Waters high-resolution instruments, this is what's known as loosening Keffelin. Here we can see just a few scans over a mass range, where yellow is high energy scan, blue is low energy, and every 10 or so scans, the instrument will focus on the lock spray, and if it observes any errors in the accurate mass, the decimal places, it makes that correction. And in that way, we can ensure that we still obtain our 1 or sub ppm mass accuracy. A final parameter from a mass spectral side, which can assist quite a lot, is improving our peak capacity by increasing the scan rate by which our mass spectrometer scans. Just a quick example here, we can see at 1 second scan, not all the chromatographic peaks have been resolved here or accurately profiled. The moment we drop the scan rate or speeding it up, we can get better profiling. And then I would now like to touch on a more novel topic, which is ion mobility. So ion mobility, for those in the audience that might be new to the concept, is defined as the movement of ions through a neutral buffer gas under the influence of a non-uniform pulsed electric field. Where in chromatography, our molecules are separated based on their retention time with the stationary phase, in ion mobility, metabolites are separated based on how they drift through this neutral gas. So to show this quick animation, we can see how we have these pulsed electric fields while the gas flow is pushing back, and our 3 molecules are separated based on their mobility. The rate of the movement, or the rate of molecules drift through an IMS collision cell, is influenced by various factors such as charge, shape, size, and 3D dimensional conformation. And this can be used, obviously, to resolve certain kinds of isomers. and provides additional information to our analysis. Finally, there's one more benefit to ion mobility, and that is the generation of what's known as collisional cross-section values. CCS is a robust physical chemical property. The same way every molecule has a boiling point or a heating point, a melting point, has a mass to charge ratio or a Dalton, it has a unique CCS value. And while most untargeted metabolomics experiments focused on the LC and MS dimension, adding in ion mobility just adds that extra dimension of richness to your analysis. And one very important thing that I would mention is that although there are many high resolution instruments that are capable of performing or implementing ion mobility types experiments or have ion mobility capabilities, the precise location of where that ion mobility cell is housed in the instrument or situated in the flight path can have a massive impact on the total versatility or the types of analysis that can be performed on a mass spectrometer. So quickly looking at the schematic, this is a schematic of the SYNAPT G2SI. We can see our molecules coming in from the LC, moving through our flight path, moving through the quadrupole, and then we have our ion mobility cell, which is nestled between the LC and our high resolution time of flight. And to illustrate the capabilities of why it's important where the ion mobility cell is housed, we can look at a traditional metabolomics experiment. So here in the ion mobility cell, we have three cells known as the trap cell, the ion mobility cell, and the transfer cell. These can be selectively turned on and off, and when they're turned on, they can either act as guides or as collision cells. So in this experiment, which is an MS to the E experiment, and here's my thumbtack to show the enhancement when it comes to DIA technologies. With MS to the E experiments, when the trap cell is off, we have a co-eluting, well, 3 co-eluting molecules coming through. When ion mobility is off, it just acts as an ion gun, they move through. And once when we choose to fragment in our transfer cell, we get a convoluted spectra. We are not sure what type of lipid it is due to the various fatty acid chains here that are co-eluting due to this convolution. But this is now where HD MS to the E, that is ion mobility enabled MS to the E, offers a great deal more of selectivity. So again, we look at the second scenario where our fragmentation or our trap cell is off. Once the ions enter the ion mobility cell, they are separated based on their drift time, and they are then sequentially fragmented one after the other. And our end result is that we get a clean and clear spectra, which we can use to make a positive identification. From a CCS perspective, there are a lot of type of molecules that co-elute that cannot be chromatographically resolved. The big example here is glucose versus fructose, where they have the same CCS, the same chemical formula, the same accurate mass down to the decimal points, but they have 2 different CCS values. Again, with leucine and isoleucine, same chemical formula, same accurate mass, 2 different CCS values. And it should be noted that these CCS values, which shown here on the right side, over a mass to charge ratio, are incredibly robust. They are independent of matrix or ion concentration. So we can move through different types of samples. If we analyze the same compounds in those samples, we'll find the CCS values remain the same. And then finally, just again to highlight, what makes ion mobility so attractive when it comes to untargeted metabolomics experiments is that in terms of the timescales we mentioned, ion mobility separation works on the millisecond scale, and it is very, very finely snuggled between the LC and the MS dimension. So briefly moving through the rest of this, I won't touch on the statistical analysis too much, but often, as said before, once we reach the midway stage where our data has been acquired and acquired correctly, we can kind of stop and take a breath. And then from there, to proceed with our analysis, we want to be able to convert our raw LC-MS data in a format that is usable for statistical analysis. The way I like thinking of it is converting LC-MS peaks into a data matrix is akin to translating one language into another. just as in language translation, getting the precise conversion is obviously crucial, it's paramount. But if we as researchers are not meticulous in the parameters, as shown here below, if we're not meticulous in the parameters that we specify during our processes, the consequences can be significant. And we end up risking that the results are not just slightly off, but dramatically inaccurate, sometimes misleading. So in that regard, when it comes to data processing, at least for statistical analysis, the generated Excel data matrix and the quality of that matrix is crucial. But quickly looking here, we have our samples on the rows and our different metabolites that are present in those samples on the columns. Obviously, this can be inverted. It's not a train smash. But the reason I say that sample matrix, I just use a different figure here, is of paramount is because we frequently use it for statistical modeling, for specifically projection-based techniques, such as PCA, PLS, and OPLSDA analysis, just to name a few. And yes, each of those models, once they've been generated, should be statistically validated in their own right. But the answers they provide are dependent on this data matrix that is generated. So during your data processing, spend some time on these parameters. As I said, you can always go back if you find that your models aren't yielding the result you want. Moving into metabolite annotation, structural elucidation is probably still the most challenging step in the entire workflow, despite advances in the instrumentation. So obviously, the first crucial step that we want is we want to get the correct chemical formula, the correct elemental composition. In order to automatically constrain thousands of possible candidate structures and to rule them out and only select the most likely and chemically correct formulas, leaders in the field, Tobias Kint and Oliver Viljoen, wrote an article where they outlined the 7 golden rules for heuristic filtering to ensure that when you move from your accurate mass to a chemical formula, that you know all the chemical formulas on that list by probability at least correspond to some sort of real or likely metabolite, at least in terms of biological samples. The moment you move into synthetic chemistry, the goalpost changes. And once we've filtered our chemical formula, what we would typically want to do is filter our elements just to limit the overall number of formulas. This is the way I do it. This can be changed. Obviously, this can be optimized or modified. So I like filtering it according to the, what are they called? The elements of life, the elements that are used to make up life. From there, we would generate our chemical formula, check our mass error, arrange it accordingly, check the isotope pattern, and then screen the most likely candidate against the library or database. Just doing that workflow up there gives you a level 4 annotation, which should be reported, should be specified during publishing or research. Once you achieve a possible hit and you can assign a structure to it, assign the fragmentations to it, we delve into level 3 or level 2 analysis. And then finally, for us to achieve level 1, we would need to compare it with a reference standard material. Something very interesting is that there are auxiliary or additional orthogonal techniques that can be used to help filter out or ensure correct annotation of molecules. The one, again, is our LC dimension. Frequently it is disregarded, but the log P value of our LC dimension or the log P of our molecules can be calculated. And based on our log P values, with the addition of an internal standard, we can monitor and check if a molecule is likely to elute where we found it, or if we might have made a mistake during our annotation. With ion mobility, generating CCS values are also very useful as an additional parameter, especially when CCS is independent of chromatographic separation or matrix effects. There are a lot of softwares out there where you don't have to start at the very beginning, and you can just generate your chemical formula automatically and screen it against in-house libraries. These are the two that I provide as an example. But the workflow is labor intensive. There is no way around it. And when we annotate our molecule, we would typically want to ensure that we have the maximum amount of biological information so that we can make an accurate identification in terms of mass accuracy, using image to the E to generate fragments. When ion mobility is available, generating CCS measurements, also providing more clean spectra, using our log P values to determine where molecules should be eluting when indexed against the internal standard. And sometimes using the isotope pattern can be a useful technology or useful piece of information for identification. The last two slides that I have, finally, when it comes down, once we've done the analysis and it comes down to write up or submit, publish your literature or your research, I would really emphasize the importance of transparency when reporting. Frequently, a lot of the information is left out. I'm not sure what those reasons might be, but at least in this case, these are the things that are listed here that you guys can have a look at, and remember that should be included in your materials and methods section, or when you are reporting or publishing literature or research. So this is the chromatography side, and here is the mass spectrometry information. And that is me. Thank you for your time.
I told you he's the best.
I hope I didn't go too far off time.
No, thank you so much, Dylan. I think it's very rare that you get someone with that amount of knowledge that can actually translate it in a way that everybody can understand it. Thank you. We already have a few questions for you.
Okay.
First of all, I've received a few messages and also emails regarding the recording. We are recording the session. We will make it available on our YouTube channel. I'm sure Microsep and DIPLOMICS and MSA will also make it available on their different channels, so on, and we will share the link in an email with all the attendees afterwards. There's another question on the video recording. You see, it was great. And I think a lot of people will be using this presentation when they train their students and fellow staff. We have a question from 𝗬𝗲𝘀𝗀𝗶cie Malloy. When you do untargeted analysis, is there recommended solvents to use, or must one have an idea of the type of compound groups expected, which then inform the solvent selection?
Yes, it is a bit of a hard question to answer, but typically we would start off with acetonitrile, methanol, LC-MS grade water, and isopropanol, and see when we use combinations of those solvents, can we get our molecules separated out? Can we get them ionized and detected?
Thank you, Dylan. Bianca, did you want to add to that?
It's just when you're looking at wide, it definitely is about your metabolite, your compound groups, because if you're starting with a wide range, you have specific combinations of solvents that you can use based on the polarity. It's your characteristics of your target analytes that you need to take into account. So reviewing literature often helps to have a starting point, depending on how broad or how specific you want to be. There are very good resources out there to calculate specific organic solvents that you can use for starting points. Ilse, I think I'll find them and I'll share them with you. When you send the mail, then you can maybe send those resources along with them as well.
Fantastic. Thank you very much. So there's also modifiers that you can add to these mobile phases to acidify or basify these to help with the eventual ionization of your compounds, and even this will change what you see. But Bianca, 100%. I always tell people to, the work that you do before you set up a method, take more time with that. make sure that when you go into the lab, you already have all your fats set up. Then there's a lot of questions as well for the presentation that we said we will share. Thank you, Dylan from Fani van Heerden. Thank you very much, Dylan, for the excellent presentation. Then we have Benjamin Abram asking, hi, Dylan, what is your opinion on new in silico annotation methods such as GNPS, NAP, and Sirius, particularly for the DIA context that you have just described?
Oh, so hi, Benjamin. I'm glad you could attend the webinar. I would definitely advocate for the use of tools like that. It does improve the identification step quite dramatically. With a lot of, rather than doing it manually where you have to sit and try and annotate 200 compounds, using softwares like these really speeds up the process. So it has, they have several benefits. However, something that should always be kept in mind is it is a software, it is an instrument, or it is a computer. It does not think for itself. It can only provide information based on the data that you have provided. It's that old adage of garbage in, garbage out. And in that respect, yes, definitely useful to use, especially when it comes to DIA, but you should be vigilant knowing, or at least supervising, looking over the answers or the results that you obtain from the software to ensure that the annotations that made are indeed correct. I know DIA, from a Waters perspective, we had some trouble converting DIA method files into universal MZML format. Thankfully, I can now say this year that Waters has attended to that issue and that we are now able to convert raw data formats into MZML for us to import it into these types of softwares.
Thank you. Then there's another question in the Q&A to 𝗬𝗵𝗲 saying, thank you, doctor, for the presentation. I have a few questions. And then there's a lot of questions. First question, which ion source that could cover all molecules, polar and non-polar, to be ionized?
Sorry, I'm just navigating to, okay. So which ion source could cover polar and non-polar to be ionized? Is there other reference materials for untargeted analysis? Okay. So yes, I would be a very good starting point. If you have APCI available, that's definitely an option. ESI or electrospray ionization does cover about, let's say, 95% of the total metabolites that can be ionized. So I would definitely advise that as a starting point. If you have more non-polar compounds, like compounds that have a lot of hydrocarbons, certain alkaloids or steroids, APCI is a very good alternative to use. In terms of the reference materials question, I'm not quite sure what's being asked there.
So I think you get reference material for targeted methods, and this is when you know the compound, so you can buy a reference material. Untargeted is much more complicated because, as we said earlier, you don't know what you're looking for.
Yes.
You have no idea what you are looking for. So what we could typically do is you take a mixture of compounds that has compounds from different compound classes at least. So there's different lipids in there, there's different amino acid, maybe a fatty acid, and organic acid. So you use these to sort of just inject that into every single sample or with every batch, just to see if you still get the same answer and response from every batch for that compounds. So reference material would not be possible for untargeted. So what we normally recommend is you do an untargeted analysis first. Then, as Dylan just said, you do your statistical analysis. So you have maybe a disease group and a control group. Which are the compounds that differs the most between these groups? You try and identify them using those 7 steps. You try to use different libraries and so on. Then when you get to a set of 10 compounds that you feel, statistically, these 10 compounds always differ between the diabetes group and the healthy group, then you can now buy the standards specifically for those 10 compounds and then just confirm. So then you will set up a targeted method. So if you don't know what you're looking for, it's not been done in literature, it's a good thing because you'll be the first, but then know that it's always just a hypothesis generating study, as Dylan also mentioned earlier. So you cannot prove a hypothesis with untargeted work. You can only generate more hypotheses, then prove it when you go to the QTOF, or the triple quad, and then you do targeted analysis. So I hope that works to show me for that answer. Then there's another. So certified reference materials, that's exactly what I mentioned now. So for example, in GCMS analysis, there's this option of using fatty acid methyl ester mix, or a mix that you know where the retention time should be, you know what the intensity should be, you know what the compounds should be. You just use that, but this is just to test your instrument. It's not. You can't trace it back to your sample, Then there's another, I don't know, do you want to add to that before we go to the next question?
Ilse, I was just looking at the time and I was going to think, for the sake of time, would it be possible? I don't know if we're going to a break now,
Yes.
or Dr. Madala is still going. And I was thinking that maybe then during the break, I could try and type out, answer these as good as well as possible. Something I could do alternatively is I could also add my email just in the chat. So if these are serious questions, that you can send the message, we can have the talk, then we're not constrained by time, because I see there are quite a few of these questions flooding in.
Yes, it's flooding in. I agree. So maybe we can go to a break. I just quickly scan through the questions. So thank you, Dylan. Those types of ones, we appreciate it. To repeat the measures now. Okay, yes, that. Okay. So my suggestion, Dylan, maybe you can copy that in the chat, because we are the only ones who can see the Q&A questions.
Okay.
So if you can maybe copy those questions into the chat and then give the answer there, that would help. There's a lot. I will help you.
I'll do that during the break. Sure.
Okay. So we can go to a quick break. Dr. 𝗬𝗲 is also saying, great presentation, Dylan. Maybe we can take a break. It's not a bad thing that we have all of these questions. I think it's a great thing. Dylan, also, if you feel that the answers would be appropriate to the wider audience, I think we can take 5 minutes and then just answer that live. Okay. So let's take a break of 10 minutes. You can quickly run to the bathroom, make a cup of coffee, get a snack, and we will then start again at 20 minutes past 12, 12:20. Where Prof. Edwin Madala will give us a real-life example of how he actually uses this instrument in his research. Okay, thank you. So we see you all in 10 minutes.
Okay.
Okay, we're back. I know it's 1 minute before. I just wanted to confirm with Dylan, is there any questions that you would want to answer live? And we also have a hand up from 𝗬𝗲𝘀𝗀𝗻𝗄. So I'm going to unmute you, 𝗬𝗲𝗀𝗻𝗄, and then you can just speak.
Hello, am I audible?
Yes, very audible.
Hello everyone. I just have a question for Dylan. It's regarding, I have a project and I set up a methodology. I'm doing LCMS. So I was advised that my sample extraction method isn't for a targeted approach, is more untargeted, and I'm doing a targeted metabolomic approach for my project. And I've added the internal standards as well as the acetonitrile, but however, they said that they advised that I should look for a more specific targeted approach for my project. So I was wondering what advice would he give to add a more specific targeted approach, because they're saying that my methodology is for more untargeted approach.
All right. Thank you for the questions, 𝗬𝗲𝗀𝗻𝗄. I'm not quite. So you mentioned the sample preparation step that you used was more targeted or more untargeted? That was the part I didn't hear properly.
Okay, let me just reiterate what I said. So basically, my approach that I had initially set up, I thought it was for I'm supposed to do a targeted approach. So, however, when my ethics application, they said when it came back that my methodology is more of an untargeted approach rather than the targeted.
Okay.
So I
yes,
should
I
look
see.
for a specific targeted approach. So I wonder what advice would you give so that I can add, because I used the specific internal standards and I added how I'm going to like calibrate.
So my suggestion there would be, well, if there is previous literature, that's always useful. Yes, saying previous literature is very easy to say. I would suggest looking in journals like Journal of Chromatography or Journal of Mass Spectrometry, ASMS, those types of journals where there is a high impact factor and you know the quality that they're publishing is high, and then try and look for a sample preparation method that they might be using there. There's usually something that can be used. The other alternative is what's known as solid phase extraction. And with that method, you can then selectively focus on certain metabolites that you want to identify or quantify. You can remove a lot of the excess matrix, and as a byproduct, as an additional step of sample solid phase extraction, you can also concentrate your sample. So if it is at very low volumes, low concentration, it does have that extra additional concentration step that can be used.
Okay.
I just want to add to that, 𝗬𝗲𝗀𝗻𝗄. So it depends on what you want to target. And if you want to target lipids, then the sample preparation is much different than if you want to target amino acids or fatty acids or organic acids. So it really depends on what do you want to target, and do you know what you want to target? Or if you don't know what you're going to target, then you should go the untargeted route as you have it currently.
Do you can you by chance provide us some information on the type of metabolites or the metabolite classes that you're looking to analyze?
Okay, so basically I'm looking at the kynurenine pathway, tryptophan kynurenine pathway.
Aha, okay.
Amino acid pathway, yes. Yeah,
Okay.
so for that, you'll get a lot of literature, like Dylan said, on amino acid analysis. There's kits that you can use for amino acid analysis that you can use to prepare your samples. It's definitely not an untargeted prep. It's definitely more specific.
Yes,
So,
but however, I used specific so when I do do my extraction part, I added that I'm going to use the internal standards at specific concentrations. So I need to look at tryptophan, kynurenine, the IDO1 ratio, and quinolinic acid, and NAD. So I used those internal standards when I do my sample extraction.
I want to just, sorry to interrupt there. Can we maybe, so Dylan added his email address there in the chat box for you. I think this is a very specific question for your specific project. So you're welcome to either email Dylan, you can also email me, or you can go to our website and add the enter the contact form. And then we can also have a different separate meeting to discuss this in more detail.
Okay.
Okay.
Thank you.
Okay. We have a different hand up, Artem. I'm going to give this the last, allow this, I allowed you to speak, Artem, and then I'm going to go to the next presentation. Artem, you are open to speak. I'm not sure if you want to. There you go. No. Okay. Artem Zarikov, do you want to speak? No. Okay. Anyways,
I see in our chat he just wrote "I want," and I think he might have gotten cut off.
But I cannot. I want, but I cannot. Maybe you should just unmute yourself, because you have our side, it looks like you can definitely speak. Okay. We'll try again later, or maybe you can just type your question in the Q&A. Okay. Thank you so much, Dylan. Is there any other questions that you picked up that you think you want to share with the group, or did you cover everything in the chat?
I'm still busy covering them, but I have covered quite a few. You guys, we
Okay.
can continue with the presentations.
Okay. So I think let's continue with the presentations, and after the entire day's work, we can take some more questions, and then everybody who wants to leave can leave, and then we'll give some more time for the presenters to answer a few questions. Okay, so our next presentation, you're gonna love this. This is the application of the SYNAPT that Dylan has been speaking about into real life research. It's often very difficult to understand this technology if you don't really see, at the back end, what you can actually practically do with it. So for that, we have Professor Edwin Madala from Univen, University of Venda. Prof. Edwin did his PhD, if I'm correct, at UJ. Please correct me if I'm wrong. And then was, I don't want to say caught, but he was swiped up by Univen to go and start the Metabolomics lab there. This is going to be a very insightful talk. Thank you, Prof, for being here today. You're welcome to share your screen and then start your talk. We will take the questions afterwards then. Thank you very much.
Thank you very much. You will tell me if my screen is shared.
Yes, I can see your screen now.
Okay, right. Yeah, that is
there you go.
wonderful.
Full screen.
Yes, thank you very much. Good afternoon to everyone, and thank you very much for the invitation to Louis and the team and yourself, Dr. Du Preez, for giving me an opportunity to come here and speak about the work that we're doing here at the University of Venda. As already been mentioned, my name is Edwin Madala. I'm a resident mass spectrometrist here at the University of Venda. Indeed, I'm a UJ product like Dylan. We scattered after UJ, and then I came back home. I was not invited back. I had to come back home because I'm from this region of the land. So I'm back here to start up a metabolomics laboratory, which has been ongoing for 5 years. We have some few gadgets in terms of the mass spectrometry instrument. We have a QTOF instrument. We have a triple quadruple instrument. The Department of Chemistry has recently bought a GCMS We also have few basic chromatographic instruments such as HPLC, PDA, UV. We have GC, FID, GC, ECD. We are building up our repertoires of analytical instruments. We have, I think, 2 or rather 3 preparative HPLC for organic people who can also prepare and isolate and fractionate different compounds from mixtures. So, but today I'm going to speak about some of the applications that we have done here to get some work that I've done while I was still at UJ and the work that I'm doing when I'm at Univen. And I chose one of the projects that we work on, which is very unique to us, which has to do with the UPLC QTOF MS-based chemical profiling of light-responsive metabolites in plants. So Dylan has already mentioned to you guys that the metabolites, or whenever you are going to start working with metabolomics studies, you must know that you are going to be dealing with high-dimensional data. And this high-dimensional data comes from these instruments like a QTOF, which spews a lot of data because at a go, this instrument can analyze between 4,000 and 6,000 compounds at a go in one chromatogram. And looking into that data requires sophisticated skills that we are going to showcase here, and some of which Dylan has already explained to you. So I'm going to use plants as a model plant, as a model organism, as we do here at University of Venda. We run our metabolomics across various samples, from environmental samples, which is water, soils. We do plants. We have started working on medicinal samples such as urine, plasma. We are doing a lot with this QTOF instrument. That just goes to show the robustness of this instrument. And then, yes, indeed, we are also building our data analysis softwares and methods in order to capture this high-dimensional data that we achieve from this instrument. So as I already said, we're going to be dealing with plant. Plant chemistry is one of the most complex sample that one can work with in metabolomics. And this is because plants produce a lot of metabolites with different physical and chemical properties. Dylan has already mentioned that, from size to polarity, all those type of things are some of the things that makes plant chemistry to be more complex. Of course, the biosynthetic enzymes or the genetic makeup of plant is what enables this plant to make these compounds, and that's why they are so complex. We human beings, we rely mostly on this plant for medicinal purposes. We take some of this metabolite and we try to treat some of the disease that we suffer from. We have seen during the COVID pandemic that most of the people resorted going back to certain plants for steaming, for drinking, to relieve the colds and the coughs. Plants compound, most of them have been developed to commercial drugs. There are a lot of drugs that are used for malaria. There are a lot of drugs that are used for as antimicrobials, for skincare, that are all coming from plant directly, that has been developed as commercial drugs. But because of this complexity that plant chemistry possesses, it is quite difficult to analyze these extracts, and you have to require high analytical skills and very high-tech instruments like NMR, IR, and LC-MS in order to comprehend this complexity of plant chemistry. So because of the complexity of the data that comes out of this instrument, as I've already mentioned, you require sophisticated softwares such as computational metabolomics tools and multivariate data models that can allow you to unearth the biological meaning of your data and the patterns within your data. So I've already mentioned that indeed plant metabolomes are complex, and some of the reason is because these plants uses these metabolites in order for them to survive in their environment. But within that environment, there are threats that makes this plant to utilize this chemistry in order to, sorry, I need to go back. I'm trying to, okay, I don't know how to do that, but it's fine. So in order to comprehend these threats that are coming from the environment, plants have to produce these metabolites. And the type of stress that they encounter include pathogens such as the viruses, the bacteria, the fungi, and all other things like nematodes, parasites, and all those things. Even us human beings, we are a threat to plants because for them, they want to survive. For us, we see them as food. For us, we see them as medicine. We even feed our animals some of the plants like as graze for the cows, the goats, and all those type of things. Plants don't like that. And the reason why, or the evidence of showing that plants don't like human beings or animals is because some of the plants, when you touch them, they do produce poisonous compound because they're trying to alert you, say, stay away from me. But of course, we as human beings, we think we are in charge of everything in the world, so we go after these plants. But these threats, like I said, including us, again, allows this plant to produce more of these metabolites to defend themselves. I've already spoken about the pathogen, the biosynthetic pathways that are indicated here. I just want to get a pointer here. The biosynthetic pathways, for instance, such as the glycosylation patterns that are conjugated into metabolites such as flavonoids, they come in different forms, and this allows these metabolites to be diversified. For instance, you can see here, this flavonoid has only one sugar, but through the glucosyl transferase enzyme, another sugar can be added. The same thing happens when we eat the same metabolites. When we try to detoxify them from our body, we add sugar, additional sugar, using the same enzyme to get rid of them. But in plant, this is done in order for storage and diversification. There are issues such as drought that causes stress to plants, and plants do respond, and some plants do respond better. In so doing, we can be able to select the line that is drought resistant, and we'll be able to look into it from the metabolite point of view, which plant respond well to drought stress. And from there, we can be able to come up with plants that can be able to withstand this type of stress. One other thing that contributes to metabolite complexity is conjugation. Some of these metabolites, such as phenolic acids, are conjugated to organic acids, such as this one here, which is the glucaric acid, quinic acid, citric acid, tartaric acid. We, in our laboratory, we have worked with all this conjugation, and we are looking into how do plants, from the biochemistry point of view, from the gene level point of view, how do they incorporate these things, and how does this help to diversify or storage of metabolites? One other stress that is coming along is heat due to excessive sunlight. And this we are going to speak in detail because, as the topic of my study suggests, we are going to look at light-responsive metabolites, how plants respond to excessive sunlight and excessive light. Another thing which is very common in plant is isomerization. There are a lot of isomers in plants. And as you know from basic biochemistry, that for the plant or when you are doing analysis of plant extract, you need to identify a correct isomer, because from biochemistry, basic biochemistry, we know certain enzymes can only recognize one specific isomer. And if the isomers are showing the same mass, the same fragmentation pattern, I mean, Dylan showed us leucine and isoleucine with a very close collisional cross-section. How do you determine which one is which? If you want an activity that is conferred by isoleucine, how do you eliminate leucine from isoleucine? So those type of things you need to have knowledge of. The stereochemistry and other chemical modifications that happens in plant metabolites and exacerbate this complexity of metabolites, and we need to find ways to deal with such. So I've already spoken that the topic of interest here today, it is on issues of excessive sunlight. So plants produce some metabolites known as cinnamic acid. This cinnamic acid, as you can see here, is produced in plants with a trans configuration. However, when this molecule is exposed to sunlight, it converts to cis isomer. You see, unlike us human beings, when we feel that it's too hot, there's too much sunlight, we can carry an umbrella. But plants cannot run away from the sunlight. What then they do is that they absorb some of this sunlight. Of course, they need sunlight for photosynthesis, but they absorb excessive sunlight and to drive this chemical modification. And we can then see it from LCMS that indeed there are two peaks that are identical with everything, but they are appearing at two different rotation time. Because the moment this change in geometry happens, these two molecules will elute at two different regions in a chromatographic space. As we know, due to global warming or due to depletion of atmospheric ozone layer, there's too much sunlight reaching Earth's surface. If you come from this side of the world in Venda, around summer, you know how hot it can be, how much sunlight we do receive from here. That means some of our plants are undergoing this process where there are metabolites that are containing cinnamic acid are converting from trans to cis. And the presence of the cis isomer is different from one region to another, depending on how much sunlight is there. For instance, if you have small plants that grows underneath other plants, those are shaded, you don't actually see a lot of cis cinnamic acid. But for plants that are exposed to the sunlight, you see a lot of cinnamic acid. And due to the effect of climate change, such as depletion of ozone layer, global warming, too much sunlight reaching Earth's surfaces, many plants are showing signals of cis geometrical isomers. And the presence of geometrical isomers is very problematic in a way that maybe it's the trans isomer that works, maybe it's the cis isomer that works. But I will tell you a little story about cis and trans isomer. For instance, in Kruger National Park, if you go there, you'll find that elephants, during the day, they eat certain plants and they don't eat certain plants. Because during the day, this conversion is very prominent. They prefer plants that have more cis during the day, and during the night, because there's no light, this goes back. So there are certain plants which the elephants do not eat during the day because the taste of this cis isomer is not good for them, which goes to show that there is differences in the biological properties of the trans and cis isomer. Hence, we study them here. So more to it is that because of the presence of this isomer, they pose a very serious analytical challenge. And as such, we need to understand, again, if these excessive sunlight episodes will continue to rise or to increase, that means plant will need to be adapted in order to withstand these things, because it will get to a point where these cis isomers will also become toxic to the plant. We don't know. That's why we study them. But we see, we can complain about excessive sunlight, but what about a plant? It is always happy. It produces fruits for us. We eat some of the plants, we eat their leaves, because they keep giving, irregardless of the stress that they go through. So we need to understand the stress and come with mitigating a solution if there's a need. So I'm going to present some of the findings from two studies that we did with one of our PhD students, Dr. Rampinywa, who has since graduated with her PhD at UNISA. I was co-supervising this project from here. Almost actually all the data in our PhD was collected at the University of Venda in our instrument here. So she did a comparison of a bush tea plant that was exposed to UV light for 24 hours in a simulated environment that we have built in our laboratory, and a naturally growing plant which served as a control here. This extract were prepared in 80% methanol, and they were subjected to chromatographic separation using a bifinal column. We use a bifinal column. Someone asked a question about column because, as you can see here, there are a lot of pi electrons here because of the double bonds that you see in the ring and also in the olefin functional group, which is this double bond here. And there's another one here. So these are very good candidates to be analyzed using a bifinal column. They do work well with C18, but we have found in one of my former master students that a bifinal column is better to separate this thing. From these two chromatograms, visually, sitting where you are or standing where you are, even from here, I cannot spot the differences. And therefore, I will then require a multivariate statistical tool or knowledge or prior knowledge or skills that I have in order to look into this data and to point out the difference. So if I move on, you will see that when I called upon the single ion chromatogram monitoring of a molecule called 𝗬𝗏𝗃𝗀𝗃𝗀𝗃 acid at MZ515, under the control, you can see there are 3 prominent peak and very other minor ones that are starting to emerge. However, when I expose the plant to UV light, look at the numbers of the metabolites that emerged due to light exposure. There were only 3 prominent, but there are more here. And this is just for a molecule called 𝗬𝗏𝗃𝗀𝗃𝗀𝗃 acid, which is known in this plant that is produced in 3 positional isomers. When these 3 positional isomers are exposed to sunlight or excessive light, they produce these additional isomers. This we can only comprehend with LCMS. I've spoken to colleagues who do this with GCMS, and they told me that you can't see the difference when these geometrical isomers are formed. Fortunately, you do see them with LCMS. You can't see them with IR. You can't see them with NMR because they do contain exactly the same chemical composition. However, it's just a slight difference due to the double bond shifting from trans to cis. That double bond shift has been shown to be accompanied by rotation time shift because it comes with polarity change. And that polarity change results in new metabolites that we can be able to see with LCMS. More to it is that, yes, I know some of the molecules that can undergo a change. But what if there are more? We opted to use this computational metabolomics tools. Someone was asking about GNPS. We went to the GNPS molecular networking, and we subjected this molecule or extracts to molecular networking with this color, which I don't know what it is, blue, I don't know colors very well, and the gray being UV treated, and the blue for now is control. And as you can see, there are metabolites that are unique for the control. Here are some of them I point. Some are shared between the control and the treated. Some are only present in the treated. Like for instance, this molecule here, it is only appearing in a treated sample, which again shows you that you can use these networks in order to sort of pictorially or graphically show which metabolites are present in the control that are not present in the treated, which are present in the treated, which are not present in the control. You can see some of the metabolites here, they are only gray. And this goes to show you that these are metabolites that are only present in the treated, or that came about after treatment with UV light, or they are only responsive to light. So in a nutshell, what I'm trying to say here is that if this plant was growing during the day, you expect to see the gray metabolites being prominent during the day, and during the night, they're not there because they reverse back, because this geometrical isomerization is not a one-way reaction. It's a reversible reaction. Trans to cis at night, they go back to trans. And we have never seen a molecule that goes to cis completely. They reach what is called photostationary equilibrium, where certain level of cis cannot be increased anymore. It remains there, and the only way is to go back to trans, which therefore suggests that some plants, though, if let's say, for instance, some of these metabolites that are formed due to light have pharmacological activity, that means we risk to see plants that are more active during the day and not active during the night. That's why sometimes certain preparations, you have to make them in amber vials. You know, some of the medication that we get from pharmacists, they come with in amber vials because they're not supposed to be exposed to light. Because if they're exposed to light, they change the chemistry, and therefore they will change the pharmacology. So we must also know that plants activity of plant extract that were collected during the day and those that were collected during the night won't be the same, as you can see from this results, that there is a huge difference between plants that are not exposed to light and plants that are exposed to light. Now, we have also went on to study stereochemistry. because this plant, bush tea, fortunately, it conjugates its cinnamic acids to different types of organic acids. In this case, it's quinic acid. In this case here is glucaric acid. As you can see here, the dicafeol quinic acid has, again, 3 main peaks. But look in the natural, in its natural form. In the same plant, when the cinnamic acid are attached to glucaric acid, look how many compounds are here. These 2 A's are representing plants that are growing in a natural settings. That means in a natural environment, natural light. However, the B's are when we expose them to sunlight. You can see again the number increases. Here is even more because of the stereochemistry of glucaric acid. We're even studying this further because we can't even able to know which one is which here. We have to now move to ion mobility in order for us to be able to do that. I have an example of a previous study that we did, which we opted to use ion mobility, and we were able to identify geometrical isomers. Because before our work, no one could even attempt to identify which form of geometrical isomers are these molecules here. This situation becomes even more complex when you have a conjugation. You have 3 cinnamic acid attached to this quinic acid, but this plant only makes 1 of them. This, what you are seeing here, is naturally growing plants that are starting to show signs of geometrical isomers. When you expose it to sunlight, this becomes even more, again showing you that light do bring upon new metabolites that are referred to herein as geometrical isomers. The same thing with glucaric acid. If it's dry, it becomes even more complex. I even tell you that some of the metabolites, we couldn't separate them using a 53-minute chromatographic method. This method here it's 53 minutes long. We couldn't separate these things. We are trying different things, different columns, but what we are now realizing is that we have to go for the ion mobility that Dylan was talking about. So this study shows that not only that light will contribute to these changes, but you will see that stereochemistry of the organic acid to which this phenolic acid are attached to also further complicates the situation. And again, I mean, we're just dealing with a few metabolites here. I said when I started that a plant can produce from around 4,000 to 6,000 compounds. And that also depends by which solvent did you use to extract this metabolite. There can be more depending on which solvent you use. There can be less depending on which solvent you use. There can be unique metabolites that you see depending on what solvent you use. There's something that I'm going to say in my conclusion, which is a little bit also adds to this complexity that we see with LCMS. And then in this study, what this PhD student did was also to compare plants that were grown using different net shading. So for instance, you use the black nets, she used the green nets, she used the white nets. The percentage here is amount of light that these nets will allow in. For instance, this net allows only 40%, this one 50%, this one 80%. And you can look that the composition of this chlorogenic acid differs between plants that were grown under different net shading, which limits how much light goes in. You can see they are more in the control. Only one metabolite maybe is missing here, which is missing throughout. But when you get to white 50% and white 80%, you can see that actually in 80%, we have all the chlorogenic acid compared to naturally growing plants. I mean, maybe limiting or controlling light that goes into the plant will also help to produce more metabolites or to sort of curtail what type of metabolites a plant will produce. This was very unique result. We have published it since. And then, of course, I've just showed the structures below here just to show you that is this the type of molecules that we were dealing with. And you see the difference between this one and this one is that this one has 2 OH group here, 1 OH group here. But what is unique is that they have this double bond which can undergo cis-trans geometrical isomerization. So this is fascinating results that we have managed to achieve. In one of my master students, we said, from the results that we have achieved, can we artificially change the plant metabolome ourselves? That means, yes, using UV light, we can induce geometrical isomerization and gain more metabolites. But we wrote a technical note to South African Journal of Botany, and we highlighted this geometrical isomerization that is induced by UV light as a plausible non-enzymatic approach to modify plant composition of plant extracts. I want to take a moment here and just say something. When you analyze plant or any other metabolites, the idea is that, or the understanding is that all these metabolites are produced by the organism that you're working with. But as you can see here, just light exposure of your plant extract can result in additional metabolites. And these additional metabolites can be mistaken to natural metabolites. And some people have made conclusion and wrongly identified these metabolites as natural, because some of these metabolites, as we have demonstrated before with one of my master students, these metabolites have a biological activity of their own. Some of them, they even add on top of the natural ones, the biological activity of the natural one. Some do not have biological activity at all. So again, this means the presence of these things can be of good, can be of bad, can be of no reason at all. Because some of them, they don't have any biological activity, or we haven't found any biological activity for now. So we take a plant extract. Here we demonstrated with using different plant extract, but here I'm going to show you with a plant extract, 𝗬𝗂𝗧𝗏, which is used here to treat internal bleeding and other things here in Venda region. So A, again, natural growing plant. B, plant that has been UV irradiated. But through LCMS technique, we can capture the entire chemical space of plant and use mathematical tools in order to unearth the differences here. Why? Because we cannot see this change visually. So we need this tool in order to differentiate between these two plant extracts. Yes, someone can claim, I can see the difference, but the difference that you can see with your eye could only be one. Let's see how much of the difference this can be using normal multivariate statistical tool. We use PCA, and this PCA shows that indeed the control samples are not the same as the UV treated samples. And using this cloud plot, you can see that there are more metabolites associated with treated, which is at the bottom. I'm sorry for the color swapping. At the bottom, you can see there are more metabolites there than there are here. But all these metabolites came upon due to light exposure. And what we have also noted is that not only the light responsive or those that undergo geometrical isomerization are changing. For instance, a molecule that is well known in plant called rutin has been shown to be depleted when you expose the plant to too much sunlight. So you can see the levels in the control, you can see the levels in the treated, and you can see that now you have less after you UV treated. And there's a slight increase of a molecule that is similar to rutin. The only difference between these two molecules is that this one is attached to a disaccharide called rutinoside, rutinoside, and here is only attached to glucose. What is lost from this one to this one is the terminal sugar rhamnose here, which is no longer here, which maybe suggests that exposing plants to excessive sunlight not only result in geometrical isomerization, but can also induce what is now maybe referred to as light-induced hydrolysis of this sugar. You can see now, this is now low, this is now slightly higher, which goes to show you that there is also another form of modification other than geometrical isomerization that takes place in plants that expose to sunlight. All this we are able to do with LCMS and these multivariate statistical tools. I also have another PhD student who have recently graduated. She worked on mesyl-2 plants. For those who knows mesyl-2 plants, these are plants that do not grow on the soil, but instead they grow on the canopies of other plants. They are referred to as parasitic plants. They grow on top of other plants, and because they are suspended on the canopies of the plants, which means on top of other plants, they are not shaded from anything. That means sunlight directly from the sun to them. That means this plant experiences so much sunlight exposure, which therefore means they need to find ways to fight this excessive sunlight. They do produce metabolites, chlorogenic acid, in high numbers. In actual fact, in my own experience, having published over 100 papers in this topic, this is one of the plants that I found to have to produce a lot of chlorogenic acid. And we have wrote a paper in Journal of Photochemistry and Photobiology where we indicated that diverse chemical modification of the chlorogenic acid composition of 𝗧𝗵𝗲𝗀𝗃𝗀𝗃 is a premise for a state of readiness against excessive sunlight exposure. Why did we say that? Because we have noted that when these plants are exposed to excessive sunlight, there's a huge shift from trans to cis. New metabolites are being formed due to this sunlight exposure. In this case here, the orange or yellow is non-treated. And again, colors problems for me. I think this is green. It is UV treated. You can see the metabolites like these ones here that are showing that are only present in UV treated samples. But this is just a subsection of some of the metabolites. In order to highlight those that were going under change, we identified some few for you to see that all of them, they have these cinnamic acids that allows them to go this change. Some of them, they're conjugated to cinnamic acid and benzoic acid. And this hydroxyl benzoic acid are known to absorb light and to limit the photo-oxidative stress that could have been caused in these plants. So all these metabolites, we have captured them with LCMS. We use these tools in order to be able to understand or quantify the changes that could be happening due to light exposure. On my last study that we did, this was a former student of mine, Ms. Mpoma, who was one of the few first students who worked on this UV light-induced geometrical isomerization. I believe, and I stand to be corrected here, that in 2017, we were the first African group to publish work on ion mobility in collaboration with a group in the USA in the Pacific Northwest National Laboratories. They are pioneers or big in ion mobility mass spectrometry, and we did share our samples with them, which they analyze on an Agilent instrument, ion mobility instrument. Some of this work we have went to repeat it at Stellenbosch University using a Waters instrument, and the results are comparable, and we think we can expand this here at Univen because we are in a process of applying to buy an LCMS with ion mobility capability. So similarly, we expose the plant extracts to 254 nanometer UV light and to induce geometrical isomerization. Of course, as we have already showed you, this is an artificial means of enhancing plant metabolome, because the plant metabolome complexity, as we now understand from these studies that I've highlighted, is not due to biosynthetic enzymes, could be due to issues such as light exposure. Using computational modeling and ion mobility mass spectrometry, we managed to identify with high degree of confidence the geometrical isomers that were formed of one molecule, which is 3.5-dicarphyl acid. And we showed that using theoretical calculations, which we did here in South Africa, we were able to determine the CCF value, and we can be able to link that optimized structure and the drift time inside the ion mobility drift tube, and that allows us to be able to identify the isomers. As you can see in this slide here, this is using a 90 centimeter drift tube ion mobility, you can see that we can be able to distinguish between all of these positional isomers from 1.3, 1.5, 3.4, 4.5, 3.5. But these are not properly resolved, even though they have slight different, slight different CCF values or arrival time. But when you increase the drift tube to 67 meters and using structure to lossless ion manipulation, ion mobility, we can be able to resolve this better. Of course, there's still improvement that can be done, but this is for positional isomers. There are some positional isomers, such as I think which one in it? I think it's 3.5, and I don't know which color now here, but 3.5 I think and 1.3 maybe that we couldn't resolve. But of course, with improvements, I think now they can be resolved. This was done in 2017. Now, we have actually found out that when you do geometrical isomerization, this is just a normal plant, 0 hour, no geometrical isomerization. After geometrical isomerization, using again a 90 centimeter drift tube, you can see that we are able to get 3 peaks that are resolved for geometrical isomerization. But when you increase the drift tube to 14.7 meters, you can then now see that all 4 geometrical isomers can be resolved properly. And this we did, this resolution was better when we look at the adduct form of these molecules, when they pick up sodium inside the mass spectrometer, which again shows us, ladies and gentlemen, that issues such as solvent and formation of adducts during ionization, these are not just mere structural artifacts. They are indeed structural artifacts, but from an analytical point of view, if well studied, they can bring upon very complex understanding of your plant chemistry. For instance, we found out that without sodium, it is difficult to differentiate between these geometrical isomers. But when they are with sodium, you are able to separate them. But normally, I've heard people say, yo, sodium adducts, potassium adducts, ammonium formates, and all those things, they are problematic in your solver, in your mobile phase, because they result in adduct formation, which hinders identification. But as you can see here, we wrote a very good paper. I think this was published in Imperfect of 9 or 10 that time in Journal of Physical Chemistry Letters, that adduct formation, it is useful for metabolite identification in ion mobility mass spectrometry. So I'll conclude. When I conclude, I want to bring to your attention that plants do produce chemicals with a lot of structural modification, requiring advanced skills for identification. Not only advanced skills, relevant instrumentation. These skills, they won't be of use if you don't have good instrument. Again, if you have good instrument and you don't have skills, they won't be of good use. One of my friends said, there's no need for you to buy a Ferrari if you know you are going to drive it 20 kilometers per hour. Again, there's no need for you to buy a Ferrari and you want to drive it 200, 300 kilometers per hour if you can't even reverse in a parallel parking. So again, you need both. You need a good car, you need a good skills to drive the project. You need a good mass spectrometer. You also need a good skills to run this mass spectrometer. What is very sad, and I'm deviating from my conclusion here, is that many universities, and I don't want to mention them by names, but if I was in charge of the NRF, I was going to go in there, take those instruments and give those to those who are able to use them. Because there are universities with a lot of instruments, but people cannot use this instrument. They come to platforms like this, speak big English, speak big words to confuse us. Even when they want to say multivariate, they will say it in a way that all of us here will be confused. But they can't do it. They have instruments, they can't run them. Some of the instruments are here in South Africa, boxed, still boxed. Why? Because people cannot use them. I've been in a place where I met someone who said their instrument was not working. I was sent there to train them. And I said, okay, let's switch on the instrument. I took a side look for something, waiting for the person to switch on the instrument. When I came back, the person couldn't switch on the instrument. But the instrument is there. They can't operate it. It was bought for 6 million rands. It was a triple quadruple instrument. So it goes to show you people that you can have the best instrument, but if you don't have skills, there's nothing you can do. And hence, you need people like Dylan. You need people like companies like Microsep, all these suppliers. Don't buy an instrument from a company that do not have experts, because you are not going to use it effectively. They are best instrument in this country. Like I said, I don't want to mention names, because if I do, I will be in big troubles, because I might need a job in those universities if University of Venda doesn't want me anymore. So same thing, this multivariate statistics and computational tools, they are effective for metabolome characterization. But again, you need skills. You need to collaborate with statisticians. You need to collaborate with mathematicians in order for them to help you to understand these things. Dylan has shown you that the companies, they've realized that because of this lack of skills in mathematics and statistics, they've built softwares that does it for you. But the results that are spewed by softwares, sometimes they need validation. How will you validate them if you don't even know, for instance, you have to run permutation test in order to confuse these models to see their robustness? These computational skills, we need people who can be able to code. People need to learn to code so that you are able to manipulate these computational tools. Now, back to my study, we can see that the formation of geometrical isomers due to sunlight exposure complicates the already complex metabolome, which requires careful technical optimization of LCMS for thorough understanding. There's a need to reconsider agricultural practices such as net shading and exposure to artificial light as a viable method to enhance plant metabolome. I know people who grow dagga, who grows them in different light settings, because they say the dagga becomes more powerful when it's grown under red light. Some says it's more powerful when it's grown under yellow light. So this artificial light exposure has an effect on the composition of a plant, and therefore it is essential that we should look at it as part of agricultural practices. I want to say this as my last point: ion mobility spectrometry. The future is on ion mobility. If you don't have an ion mobility mass spectrometer in the next 10 years, I tell you, you'll be left behind on your own. It's like if you go to Sandton and stay in Sandton and you drive a Tez, everybody's driving a Lamborghini, a Ferrari, there you rock up with your Tez in Sandton. No, in the next 10 years, people without ion mobility are not wanted in Sandton. This is going to go with publications. You will be needing this ion mobility. That's why Dylan is presenting this thing. He's not selling it to us. He's showing us what the future holds. There's a metabolomics conference starting, I think, this week. Our colleagues are flying now. They flew it at 9 o'clock to Japan. You will see almost all the work there will be based on ion mobility. We need to, in this country, to start investing in ion mobility. I know Dr. Du Preez, they have a SYNAPT at Noordwes-Universiteit with ion mobility. University of Pretoria has one. Stellenbosch is big. UJCSIR, they have one. There are many of them in this country. So it's time that Venda has one too. And with that, I just want to thank my students who have since graduated. Dr. Rampinho last year, Dr. Moyo just 2 weeks ago, she graduated with her PhD. Anza is writing up her PhD. Mpo is finishing her PhD at Oxford University. Mr. Mbezi, I've given him to Alvaro, who also has an ion mobility at TUT, and my collaborators for these projects that I've just indicated here, Dr. Mhlongo, Dr. Matumu, Dr. Tugizimana, Professor Mdau, and of course, my host, University of Venda, for the finances. With that, thank you.
Thank you, Prof. Madala. We need more people like you. You're very set in what you believe and a good marketing strategy there for Microsep. I think they should bring you some muffins after this at least.
Louis, listen. Louis here, he owes me big time
Louis,
because
listen.
yeah, I'm busy sitting here writing an NEP. It's complete, and he didn't warn me how difficult that thing is. So he owes me twice now.
Thank you. That was very insightful. I think metabolomics is actually much more complex than you ever think it is. For us working in human metabolomics, every time I see a plant metabolomics talk, I could have just as well gone to a physics talk on nuclear bombs or something, because for me it's brand new. So, but this is great. Thank you very much.
Thank you.
We are a bit out of time. So what I'm going to do is Dr. Liam Bell has to go very soon. So I'm going to give him an opportunity to do his quick talk about DIPLOMICS, and then we can do the questions afterwards. You're also welcome to add your questions to the Q&A and to the chat. Dylan did answer all the Q&A questions in the chat that was due. So if there's any other questions, please add it there. There is a few questions, but we will just get to it after this talk of Dr. Liam Bell. So Dr. Liam Bell is from DIPLOMICS. He's representing DIPLOMICS today, even though I just told him before this, he wears a lot of hats, different hats. So I'm not going to elaborate too much because I think your talk is specifically about those hats that you wear and about what you guys do in DIPLOMICS throughout the country and abroad. Thank you. I can just say this, that Dr. Liam Bell is the, is it the head? What do you call it? The coordinator for proteomics and metabolomics within DIPLOMICS, but also, as I said, he has a different role. Yes, coordinator. So thank you, Liam, for being here. Thank you. It already looks like a great presentation. Thank you.
Great. Thanks, everybody. And thanks, Ilse, and specifically Metabolomics Society of South Africa for creating this opportunity, and to Microsep as well for, I think, backing it. It's always nice to see that when these ideas kind of come together, that you know, they don't just happen. They take dedication. They do take a bit of money as well. So thank you to the organizers and the people who've backed it to make it happen. So I'm here to tell you about DIPLOMICS. Some of you may have heard the term, some of you may have not. It's not diplomatics. It's DIPLOMICS, which stands for Distributed Platforms in Omics. It's a national research infrastructure program, which is housed within the South African roadmap for research infrastructure roadmap, which is SARIA, which is then funded through the DSI. And the goal behind DIPLOMICS is to connect world-class research facilities or omics research facilities with the researchers in South Africa. Within DIPLOMICS, there are three main streams. So this is the South African Research Infrastructure Roadmap. There are three main streams. There's the genomics stream, there's the proteomics and metabolomics stream, and then there's the bioinformatics stream. And this really covers a lot of the bases around omics-based technologies. Proteomics and metabolomics stream tends to work together because we both tend to use mass spectrometers. And then bioinformatics is kind of what underpins everything. You can't do any of these types of things if you don't have good bioinformatics resources and infrastructures in place. If you, let me just do this and see if I can get that to work. So if you take a look down at the bottom here, so some of the resources that are available through DIPLOMICS are Clarity, which is a bioinformatics resource, which I'll touch on a bit later. Then there's some high impact, high visibility programs, one of which is 1K SA, which is a biogenome project, and 𝗬𝗲, which is an idea to see if you amalgamate labs, if you get more out of the sum of their parts. But I'll go into a little bit of those as well. So at this point, I'd also like to kind of focus on what is it that DIPLOMICS is attempting to do. So DIPLOMICS, it's very difficult to think about what does a research infrastructure do? I mean, that's not something that you can describe very easily. But what you can try and think about is impacts that infrastructure can create. Some of these impacts are quick and easy to get to. So you can buy an instrument and you can place it somewhere, and that's a quick and easy measurable, right? Some of them are a little bit more difficult to kind of measure, and that's over the period of time that instrument is there, how many people manage to graduate, or how much were any companies formed from IP that was developed through running data off these instruments. What about the people who are the vendors that supply these things, you know, that you're supporting this whole industry around these things as well. So these are all either sort of direct or indirect impacts, and they happen on a scale of time. All I'm trying to convey here is that there's a complex ecosystem that forms around research infrastructures, and it's not always easy to understand what it is that they're trying to achieve, in terms of, you know, you can't just take easy metrics on these things. So I just wanted to kind of point out, there's the omics and infrastructure side, and then there's the people who make use of all of these things. So Prof's talk now really hit home for me in that you can spend money on instrumentation, but if you don't have people who are effective at using it, you're dead in the water. And the analogy I always use is if you've got a Formula One car without a Formula One driver, it's useless. You're not going to get anything out of that. Likewise, you can have really good people, but if you don't have the infrastructure to empower them, you're also not going to be in a great place. So we've got to try and marry these two things together, and find what works best. Don't know if my slides have frozen here or not. Okay, so DIPLOMICS works as a network. Within the network, there are, from the genomics side, there's a number of genomics labs, as you can see here, across the country. These offer a bunch of different services. So I should, at this point, say that DIPLOMICS doesn't really have a restriction on how you can become part of the DIPLOMICS network, except for one very key important thing, which is that you have to offer services externally. If you've got a piece of equipment and you're making use of that equipment for your own personal needs and gains, or for an isolated institution or something like that, DIPLOMICS is not going to be able to incorporate you into their network. DIPLOMICS is essentially trying to create all of a network of research infrastructure across the country that specializes in a bunch of different things, that is accessible to all of the researchers in the country, and accessible to, at a decent fee, give you high quality data at a good turnaround time. These are kind of the implicit needs that have to be met. So Dr. Shane Murray is effectively my equivalent. She heads up the genomics side. She's the lead genomics coordinator for DIPLOMICS. So you can see her email address here if you need to contact her. But I'll get on to where multi-omic studies become important. Within the proteomics and metabolomics side, the main labs at the moment are, there was an amalgamation of the proteomics unit from the CPGR and the IDM to form Decipher. I manage the Decipher hub. And that's been an interesting experiment in terms of, I was mentioning, becoming more than the sum of your parts. Here's my team currently. A lot of labs might see each other as competition. But if they can start to work with each other, what can happen is you, instead of having one piece of instrument here and one piece of instrument there, and you've got slightly overlapping or even complementary sets of capacities, if you can merge those together and you can have the people who run those who can bounce ideas off each other and help each other, and you get the volumes of samples going through them, you get to a point where you can start to create a facility that is self-sustainable. And then what do I mean by that? Well, it doesn't have to look for funding to be able to employ its people, to afford its maintenance, to pay for the reagents and things that it uses when it delivers its services. So, and you know, if it can get big enough, then maybe one day it also doesn't need to look for funding when it comes to purchasing instrumentation. So that's the experiment that's happening with Decipher. And then there's the Noordwes-Universiteit, which houses the Center for Human Metabolomics. And there's a proteomics facility at the CSIR. So that's all part of the proteomics and metabolomics network. I should mention at this point that we are actively considering how we can expand this. And we are going to be in communication with the Metabolomics Society of South Africa on Ilse could perhaps provide a bit more detail on that. And then Clarity is the bioinformatics sort of service. I always think of this as Airbnb for bioinformaticians. So if you are a bioinformatician and you are looking to kind of find a job as a bioinformatician, you could apply to Clarity to offer your services. If you are not a bioinformatician and you need the services of a bioinformatician, you could go to Clarity and you could try and find bioinformaticians who can help you with what you need help for. Dr. Patricia Swart, whose email is here, is the lady who runs the bioinformatics sort of branch of DIPLOMICS. And I always think about it in the sense of a lot of people, particularly in the genomic space, but a lot of people tend to go out and do their experiments, get their data, and then go to the bioinformatician and then go, okay, please help me make sense of this data. And the problem there is they probably wasted their money because they haven't designed their experiment properly to start off with. And so I always think about the fact that you wouldn't jump out of a plane without a parachute. Why would you start an omics experiment which has high complexity without consulting with a bioinformatician first, or at least somebody who can understand power calculations and those kinds of requirements? So I can make all of these addresses available, and indeed this slide deck as well, if anybody needs these things. So DIPLOMICS tries to wrap up, is increasingly, so DIPLOMICS has been around for about 7 or 8 years now, and is increasingly maturing from just trying to create resources, infrastructural resources, to more of a programmatic approach. So where you have these big programs that encompass training and community outreach and method development. It's important to note at this point, none of this here is about funding research. So DIPLOMICS has been given a very strict mandate that it cannot fund research. It can fund method development. It cannot fund research. That's the scope of the NRF. So just to be aware of that. But yes, training, getting people, whether that's users of equipment who need to understand latest techniques, or whether that is people who want to make use of the services that are available through a service provider and need to understand how that works. There's a need for training on both ends of that, which builds a community of practice around these techniques and pipelines. And then oftentimes what will happen is there's new things will happen and there will be a need for method development. So on that note, the Center for Human Metabolomics has done some method development around lipidomics in conjunction with Microsep, which is something that sort of was supported by DIPLOMICS. One of the other big high impact, high visibility projects is 1KSA, which is a biogenome project. And this is really quite an interesting project where we're looking to create like draft genomes of a bunch of different organisms that are unique to South Africa. And this is kind of like the starting block for so creating effectively what becomes a digital infrastructure. And so researchers can access this, can look at it and can say, we have preliminary data that shows X, Y, and Z. We'd like to apply for funding that can help us to do a lot more than just this. But at least that's the starting point to enable that. So DIPLOMICS is really trying to be seen as an enabler of research within South Africa. But the one I think that is most interesting for everybody on this discussion, or not everybody, I should say that one of the things that is big in the biogenome project is looking at a number of different species, but there are also a number of plant species involved. And I think one of the next steps is, once you've got sequences, you can then move on to the proteomic space, which can also naturally sort of lead towards the metabolite space as well, which I see as being of potential interest and use for a lot of you on this forum. What would also be of interest would be the _𝗿 initiative. So this is a rare diseases initiative that is being driven by Chris Forster from the Center for Human Metabolomics, although now he's completely dedicated to _𝗿. And this is around the idea that many rare diseases go completely undiagnosed, and how can we use new age omics-based technologies, whether they're genomics, proteomics, or metabolomics, to help diagnose people. And once they're diagnosed, that you can then move forward to potentially help with treatment. So this is a massive undertaking, and is a DIPLOMICS initiative. So one of these high impact, high visibility projects that is allowing us to, through these projects, look at how do we train doctors in terms of the right ontology to write up diagnoses on what they're seeing. How do we train lab technicians on new methodologies to be able to do these new assays that then go to the doctors, who can help interpret that with the help of bioinformaticians, who have to create resources around how do you keep all of this data and make it accessible, but also in a way that is POPI compliant and all of these things. So it's a really incredibly complex, high impact, high visibility project, but ultimately I think has great value within the precision medicine space in South Africa. And then training. Training is a massive part of what DIPLOMICS is trying to do. Whether that is, we work a lot with an NPO called 𝗬𝗪 Youth. So this is around youth from previously disadvantaged backgrounds, being able to access, these are grade 11 students. They come in, we can give them lectures on genomics, which correlates to what they're learning, sort of Mendelian tables and things like that, dominant and recessive genes, all those kinds of things, and then do demonstrations with them on extracting DNA from strawberries or something like that. But get them to kind of see that science is a real thing, and maybe that's something that they want to continue with. And so that's one end of the spectrum. And the other end would be, you might study at varsity, you might do an undergraduate, postgraduate, you might struggle to find a job. There might be, through these high impact, high visibility projects, they might need people as interns to help with development of certain things. And there's ways that we're trying to address different blocks in that whole spectrum as well. Sometimes that's done directly through DIPLOMICS, sometimes that's done through the high impact, high visibility projects, and sometimes that is done directly through our partner labs. we're looking to engage with the Metabolomics Society of South Africa to see what opportunities exist within that space as well. So on that note, here you can, so this is a link tree, you can scan that, you can get access to all of our socials from there, access to our website and emails and all kinds of things. So I will leave it at this point. And if there are any questions, I'd be happy to answer any of them.
Thanks, Liam. Great overview. Is there any questions on DIPLOMICS? We can also get back to questions on DIPLOMICS after the next talk, which is the last one. I think people are getting very tired. Liam, I don't see any questions. I think let's keep it, because I'm going to actually just add to what you've said and just give an overview of the National Metabolomics platform and the CHM and so on. So I'm basically adding to what you already have done, and then let's open the floor for questions then after that, if that's okay with you.
Perfect.
Okay, perfect. Thank you. So finally, it's my turn to give my presentation. I hope you're all still awake and you can quickly run to get some coffee if you want to. I'm just going to share my screen. My talk is not going to be very technical. It's just going to be more of an overview. Just get it there. So now I'm struggling to find my own screen. There you go. Okay. So is there anyone still there who can give me an indication if you can see my screen properly?
I can see your screen.
Thank you, Bianca. Am I in full screen mode? Right. Bianca, am I in full screen mode currently?
Right, yeah, we can see your whole presentation, yes.
Okay. So what I am going to do, I'm just going to give over to my best friends at YouTube, and they will give you an overview of the Center for Human Metabolomics. As Liam mentioned, the Center for Human Metabolomics is a partner lab of DIPLOMICS. So they assisted us in making this lab profile very professionally. You can go to the DIPLOMICS YouTube channel or to their website, and then you will be able to see their lab profile videos similar to this one for all the other labs. So I'm going to show you this quick video, and then I'm going to just continue after that.
$300 million people are living with a rare disease around the world. Many of these diseases start from birth and go...
Oh, Yeti, sorry. Don't know what I did now. Let me continue.
$300 million people are living with a rare disease around the world. Many of these diseases start from birth and go undiagnosed for many years. This medical journey places huge emotional and financial strain on the affected families and the healthcare system at large. Diagnosing rare disorders requires a specialized method called metabolomics. This is the in-depth study of metabolites, the smallest and most responsive compounds of any biological system or cell, and how a biological system interacts with an external environment. The Center for Human Metabolomics, a DIPLOMICS partner lab based at the Noordwes-Universiteit in Potchefstroom, specializes in the diagnosis of rare metabolomic diseases and provides analytic services for a range of clinical and research projects within the South African health and agricultural sectors. The National Metabolomics platform, established by TIA, is also hosted at the CHM to create a niche area for social economic upliftment using metabolomics. Professor Chris Forster, a chemical pathologist and the director of CHM, has a passion for metabolomics and the ability of this field of science to provide diagnostic answers to difficult and rare medical conditions.
We do a lot of different kind of research here, but our passion really is rare metabolic diseases. So every day when I get up, there is an opportunity to potentially diagnose a patient with a rare disease, and in many of these instances be able to advise on treatment that is required, and in that way make a profound impact on a rare disease patient's life. Our main service offerings are contract research services, method development, particularly small molecule method development, and then also diagnostic services for inherited metabolic diseases. And in the newborn screening program, we screen newborns for dreaded diseases for which a treatment is available that will have a substantial impact on their quality of life if the treatment is started in time. So what we have done is we have taken our competency in small molecule analysis that has always been applied to rare diseases, and we've just shifted it and started to apply it to other areas that is also of importance to South Africa and to society at large. For example, livestock optimization, also crop optimization, drug development, food security and safety, quality control, and so on. And I think metabolomics is a very fast growing field with huge application way beyond medicine as well. So we would like to play more of an enabling role in future capacity building, training, enable more people to do metabolomics themselves. Potentially, we would also like to be more involved in method development, assisting people in setting up methods that is of use to their particular research or industry needs, and assist the market in that way.
For more information, please contact the CHM using the contact details provided or visit the DIPLOMICS website.
Sorry about that. I'm a bit technologically disabled. So what you see in the video and what Liam said is that we are the only metabolomics partner lab of DIPLOMICS currently, and we are actively searching for more of these partner labs in the metabolomics field. We already have quite a few genomics projects and genomics partner labs, but the metabolomics is a bit lacking behind. So if you feel that your laboratory can be a partner lab in DIPLOMICS, please contact me or Liam or any of the speakers today, and then we can have a conversation from that. So who are we? We are the Center for Human Metabolomics at the Noordwes-Universiteit. Where did we come from? In the 1980s, we had a guy here called 𝗬𝗲𝗄𝗏. So in that time, he was called 𝗬𝗲𝗄𝗏. He's now referred to as Professor 𝗬𝗲𝗄𝗏, meaning the inborn metabolic disorder expert in South Africa and the world. In the 80s, he did his PhD in isovaleric acidemia, and he had this thought that he could diagnose these patients using a GCMS. So he then borrowed a GCMS from the chemistry lab, and he got some patients from the local hospital for people with mental disabilities, and he was then able to diagnose isovaleric acidemia. This initiative just grew and grew from there, and it started to be recognized in South Africa as the Potch Laboratory for Inborn Errors of Metabolism, or PLIM. And I have to tell you that many of the clients and the doctors that we still help today refer to us as PLIM. So PLIM was a lab providing the diagnostic service within the biochemistry department of the then Potchefstroom University. In 1999, newborn screening was added to the list of offerings. And so what happens is PLIM, or the diagnostic laboratory, you have a patient with a phenotype and symptoms. The doctor sees this patient. The doctor thinks to himself that this might be a metabolic disorder. He then sends samples for us to diagnose. Newborn screening, on the other hand, the patients are not, or the clients are not really patients. These are just typical newborns. A few days after birth, we take a drop of blood from them, and we then test these newborns for 22 different metabolic disorders. The reason you want to do that is you want to, sorry, as I said earlier, I'm at home with the school closing earlier. So what you want to do in newborn screening is you want to catch these disorders very quickly, because in many of these cases, you can either treat them or you can stop the phenotype from developing. If you can start treatment immediately, you can prevent severe mental and physical disability in many of these cases. So I really urge you to go to our website, the National Metabolomics platform, .co.za, go to newborn screening, and there's a little video there showing you the impact of newborn screening on these babies. So if you do newborn screening, you can diagnose patients early, even before any signs and symptoms. You can start treatment, and you can literally change the life of these babies. In 2007, the university had a restructure, and this entire department, which was previously known as the Department of Biochemistry, having the PLIM and newborn screening labs fitted into that, became a center. A center is focused on a specific thing. So it's not just biochemistry, but it was focused on human metabolomics. So this whole department was then changed in 2007 to the Center for Human Metabolomics. Around 2011 up to 2014, we had a lot of discussions with the DSI, the Department of Science and Innovation, and through TIA. You can see the little TIA logo there at the bottom, the Technology Innovation Agency. And what they wanted to do is, through the government, they wanted to drive innovation from science. So you have, they actually wanted to develop businesses and business models and projects from scientific endeavors. So they wanted to start a Omics initiative in South Africa as well, where they say, let's bring Omics to South Africa, let's provide it as a service. And for metabolomics, they then chose the Center for Human Metabolomics as their first choice to host the National Metabolomics platform. So in practice, the National Metabolomics platform is hosted at the Center for Human Metabolomics. Although it's not a different entity, it's not a different functioning, it doesn't have different staff. It's the same people working there, but the National Metabolomics platform has this drive to bring metabolomics to all South Africans and Africans and any international client who wishes to use metabolomics as a service. And we will get to that a bit more later. But what we do is we provide a commercial service to clients using metabolomics methods. This became quite a big thing, and in 2015 the decision was made then to split the commercial side from the academic side. So the focus area for human metabolomics was then split off from the center, and the center is now the main commercial entity. The center focus on the focus of the center is on diagnostics, newborn screening. You can see there on the right-hand side, there's the services we offer is newborn screening, but I'll get to that now a bit more. Just for practical purposes, the focus area is where you will be taught as a pre-graduate student. So if you apply for a degree in biochemistry, you will study in the focus area of human metabolomics. They have a very strong research focus, and most of the research focuses or uses human metabolomics methodologies and insights. These are where all the lecturers and professors are sitting. So they have a strong pre-graduate training facility and modules, and also research and postgraduate studies are being performed there. The center, on the other hand, is a commercial entity. We render a service based on our expertise. We are two different entities within the faculty. We have two different directors. We are completely, in managing perspective, completely two different aspects, although the names are so similar. So I just wanted to get that out there. In the center, we also do have postgraduate students that we train. We do not train any pre-graduate students. We do not perform any classes pre-graduate level, although we do a lot of teaching and learning like we are doing today. So teaching and learning based on, outside teaching and learning, if I put it in that way. So trying to get metabolomics out in South Africa. We also train a lot of doctors and medical practitioners, such as nurses and midwives, pediatricians, chemical pathologists. We train these people to understand metabolic disorders better so that we can diagnose more patients. Professor Chris Foster is the director at the CHM. He's a chemical pathologist by trade. As Liam mentioned earlier, he has stepped down from this position for a while now. So his temporary focus is the 𝗬𝗲𝘀𝘀𝗶cie project. The 𝗬𝗲𝘀𝘀𝗶cie project focuses on the diagnostics of undiagnosed patients, and I'll get to that a bit later. So at this point, I am standing in for Professor Chris Foster as the acting director at the CHM, while Professor Ruan Low is the director at the focus area. So I always tell people that, if you want to make use of a service, contact me. If you want to enroll for a degree or a master's or PhD, you contact Prof. Ruan Low. Okay, so the National Metabolomics platform, just a bit more out of that. So this is the full commercial side of the CHM, and this is what we trade under. This is what we are known for. Please go to the website to find out more about the National Metabolomics platform. It is nationalmetabolomics.co.za. You'll see there at the top that our services that we provide is diagnostics, as I mentioned, is where a pediatrician or a pathologist would have a patient, and they would contact us and discuss the patient and send the samples, and we do the diagnostics. We do receive these samples through the normal pathology routes. So we receive them through AMPATH and Lancet, Vermaak and Vennote, Pathcare, and also from a few private labs. So you cannot send a patient sample to us directly. We also, in that purpose, we function actually as a pathology laboratory. So we have an entire sample reception area where we administrate the patient files, just like you would see at a typical pathology lab. We have our diagnostic laboratory, and then we have people who can sign out. These people are registered with the HPCSA, as I have there on the left. So the Health Professions Council, they are either chemical pathologists, medical technologists, medical scientists. So they have the license to diagnose patients. We also have newborn screening. It's the same setup. Newborn screening is also received through pathology laboratories. So if you are having your baby, you can contact us. You can contact us on WhatsApp. We have a very advanced WhatsApp communication thing going on. You can go to the website. There's a contact form. You can fill out your baby's details, and we will make sure that you get all the information that you need to screen your baby. We also have the biobank. The biobank is the only biobank in sub-Saharan Africa specifically dedicated to rare disease patients. So, this biobank is a repository for rare disease patients, and it can be accessed by researchers particularly. So in this instance, I think the audience, we have more researchers. So if you wanted to do a study on isovaleric acidemia, you don't know where to get patients, or samples, you can contact our biobank. If we have the samples, we can share that with you. If we don't have the samples, we can assist you in getting samples or recruiting patients. So that's one of the main service offerings, but it is for rare disease patients specifically. So we do not, for example, have a cohort of TB patients or HIV patients or the more typical things or infectious diseases at all. We are also proud to have the person who is in charge of our biobank. The head of the biobank is also the director at large for ISBA, the International Society of Biobanks. So she's the director for Africa and Southeast Asia for the International Society. She was also asked by DSI to start 𝗬𝗲𝘀𝗀𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃 charge of 𝗬𝗲𝘀𝗃. So we really have a leading biobank there. Then we are also affiliated very closely with Rare Disease South Africa. It's the patient advocacy group, Metabolomics SA, as we see today, and the International Metabolomics Society, and we're a DIPLOMICS partner lab. Then to get to project analysis that we have there. So project analysis is basically that we can take all of these expertise that we have in metabolomics, all the methods that we use diagnostically. You know, these are diagnostic methods. It's validated over and over for diagnostics. And we apply those methods to your project samples. So project analysis is you sitting in University of the Free State, you have a project, you have a PhD that you're doing, you want to do some amino acid analysis, you can then send us the samples, we do the amino acids for you, and we send you the data. So it's a service that we provide with the intention of giving access to metabolomics to everybody in South Africa. You don't need a lab to do metabolomics in South Africa. You don't need an eye mobility instrument, as we heard in the previous round. You do need it if you want to do that as your main research focus. But if you just want to do a little bit of metabolomics in a bigger project that involves more genetic testing, for example, or cell culture work, or whatever that is that you might do, you want to do a little bit of metabolomics, you send the samples to us, we do the analysis for you. So the project analysis principle is the principle on which this entire training of today is based. We want to give you access to the project analysis and how it works. We want to enable people to do metabolomics. And, you know, the reason that we are collaborating today with DIPLOMICS, Metabolomics SA, and Microsep is because those three companies, or not companies, those three entities and the National Metabolomics Platform all have the same exact goal, the goal of getting metabolomics out there in South Africa, making it available to everyone, even if you don't have 20 million rand to buy a fancy LC-MS, you can still do top quality metabolomics, and you can still have access to these functions through the project analysis portal, DIPLOMICS MSA, and Microsep. You can scan the QR code there at the bottom if you want to go to the website. Otherwise, you can just go to the website later. So to come to the next training event. So today was the first event of 3 in the session. Today, we wanted to give you an overview of LC-MS, an overview of metabolomics, how you can incorporate that in your own work, and so on. The in-person training event is very exclusive. We're only going to get 6 participants to participate in this in-person training. Why would you want to do the in-person training? Because you will get hands-on sample preparation experience. You will get hands-on LC-MS analysis experience. You will be able to analyze 20 samples for free using the the project analysis route at the NMP. You will be able to network with the Noordwes-Universiteit staff and researchers, and that includes not only the National Metabolomics Platform and the CHM, but also the focus area. So you'll be able to connect with the researchers in the focus area and establish collaborations there. You will be able to see how metabolomics can be used in a commercial entity. I always get the question from students, what now? How now? What can I do now after my degree? What does it mean? You can be an entrepreneur in metabolomics if you can take what you've learned in your PhD and your MSc and apply that in a commercial sector. If you come and visit us, we can show you how metabolomics is used directly in commercial activities. You will also be able to, after you've analyzed your own samples, to get intensive data analysis training, not using example sheets, but using your own data from your own samples. Okay, so how does this work? Basically, we want you to, so it will happen in Potchefstroom at the CHM in person. 6 people will come and visit us, but there's a catch. This is only for senior researchers or technicians. This is not for students. This is very important because we want to provide training to trainers. We want to show you what we do, and we want to show you how we analyze your samples so that you can go back to your own lab wherever you are, and you can translate that to your students or to your staff. So you need to be a senior researcher. It means that postdoc level or higher, or a technician. Technicians are becoming more and more important in South Africa. They are becoming the cornerstone of analytical knowledge, and they transfer this knowledge to everyone working in the labs. You can only apply to use urine or blood. Unfortunately, not any plants and not cell cultures. So this is for mammals. So it doesn't have to be human urine. It can also be elephant urine if you have some lying around, but it's only for urine and blood samples. Unfortunately, because this is what we do at the CHM, we are really going to try hard, and we already had these discussions with DIPLOMICS that we can redo this entire thing on plants using someone like the University of Venda, where they really specialize in plant research. So you would have to write an application to be chosen as one of the 6 participants. In this application, you would need to tell us what your current position is and what's your current interest in research. Some information on your research project. And if I say research project, I mean this exact urine and blood samples that you want to come and analyze. You need to tell us what that's about. Is it urine from patients with malaria and controls, or what is this about? What is the project about? You need to have ethics approval. I don't want people to come to the lab with samples without ethics approval. It can just lead to difficulties in future. You would have to tell us how metabolomics analysis would strengthen your study, how you personally will benefit from the training, and how you will be able to relate this training that you receive to others. In other words, are you in a position to train students? Are you a supervisor? Are you a technician working with students? How will you relate that? And then also, will you be able to cover the cost of traveling to Potchefstroom? So if you're coming from Venda or you're coming from University of the Free State, how will you cover the cost of your traveling to Potchefstroom? That's the only cost that you have to cover. We will then receive all of these applications, and Metabolomics SA will appoint reviewers who will evaluate the applications and come up with 6 names that we can choose. Okay. That's the technical part. The practical part is you will have to cover the cost of traveling to Potch, but everything else will be covered. And so we've got you covered for accommodation for the 2 days, the meals, the cost of the analysis, in other words, reagents and chemicals, the use of the instrument, all training costs, training material, everything else that goes with it will be covered by DIPLOMICS, Microsep, and the NMP. The deadline for submission is 15 July, so it's more than a month from now. So you have enough time. And we will send you all of this information in an email to all attendees afterwards. If you are a student attending and your supervisor couldn't be here or your lab technician couldn't be here today, you're more than welcome to send the invitation to them if they wanted to apply. And we are then looking forward to seeing you in Potchefstroom. We will have representatives of DIPLOMICS Microsep there at the day. And I just wanted to say that you will get training, as I mentioned before. Dr. Dylan Zeiss, the expert on SYNAPT in the country currently, will be the person who will provide the training in the lab. And we will also have some people from NMP there and people from DIPLOMICS. But don't worry too much, because we will document this on a video. We will share the video with everybody afterwards. We are considering a live stream depending on the interest that we receive. So even if you're not in the lab, you will be able to take part in this. And then the best of all, we will have a third training session as well in August. So 2 weeks after the in-person training, we will have on 27th of August, perhaps also the 28th of August, we will have an online data analysis training. The 6 participants who analyze their 20 samples will be able to analyze their own data in this training. And this is what Dylan mentioned is the 7 steps, how to analyze your samples, how to make sure it's good quality data, how to do statistical analysis, how to identify biomarkers, how to annotate the markers, how to be sure that it's that. That will all happen. You can use your own data from your own samples for that. But everybody else is also very, very welcome to join the 3rd session. We will provide you with a training data set. So even if you were not one of the 6 participants, you will also have the opportunity to get in-depth, hands-on training in data analysis of SYNAPT data. I hope I covered everything. I'm going to just stop talking now, stop sharing my screen. Sorry, it's a bit difficult to be the facilitator and the presenter. So unfortunately, there's a question from Ntakadzeni. We will not be analyzing tissue samples in this round. It's only for urine and blood, because that's the methods that we have currently set up. And if we have to do it on tissue as well, it's going to be a bit difficult. But we can do that in future. Okay, so if you have any questions now for Dylan, any further questions for Professor Madala, we're going to get back to the questions previously asked. If you have questions about DIPLOMICS for Dr. Liam Bell, NMP for me, the 2nd session, you can ask the questions now. Let me just get back to, okay, so I can't remember, we had someone who wanted to unmute themselves that we couldn't do previously. I don't see the hand. So, Professor Madala, there's a question for you from Sinthandile. Hi, Prof. It's very interesting observation, more especially the UV-induced concept on your plant chemical composition. I would like to know if there are health-related benefits of the new compounds forming after UV exposure. Prof. Madala, are you still there? Okay, I think he may have left to make some coffee.
Bio break.
We will get back to that question. I'm sorry. Sinthandile. Okay, Ivan is asking, thank you for the opportunity. Please, can you share the requirements, then we can apply? Yes, so definitely we are going to share, we have all the details of everybody who attended, and we're going to share the details, well, in more detail, the requirements that you need for attending and applying. I think tomorrow at the latest, we will send that to everyone in your email box. We will also add that again to all the LinkedIn profiles. So I've said this quite a number of times, but please please like DIPLOMICS, the NMP, National Metabolomics Platform, and Microsep on LinkedIn, Facebook. Go to the websites. I think if you like the LinkedIn pages, you would probably get the most information on there and different opportunities. Can you please make a copy of the Q&A session as a transcript? I think it would be useful. I also think so. Yes. So we will get a report from this where all the Q&As will be on, and we will send that on as well. The recording will also be sent in a link. Okay, we are a bit over time. I have to say thank you very much for everybody attending. I think the fact that we are over time just shows the massive interest in this topic. And I really wish that, or I know that next year we will do this and it will be even bigger and longer with more speakers, more breaks. We might send you a cup of tea in the middle. Yeah, this was to test your interest, and I'm really blown away by the interest. I think all the other speakers as well. We are blown away by the interest, and we will, according to this, I think we will definitely continue with these sessions. Prof. Madala is back. So I'm going to ask you your question, and then I'm going to ask everybody, please email your questions that you have. We are over time, so if you have any other questions, you can email that. You can also go to, if you don't have an email address and you're not good with memory of email addresses, go to the National Metabolomics website, National Metabolomics Platform.co.za. There's a contact form. If you fill out that contact form, it will route to me directly, and I will then route all your questions to the person that it was intended for directly. Okay. So Professor Madala, we will quickly go to your question, and then we will ask Professor or Dr. Sitole to close. I don't know where that question is now. Or maybe, Prof. Madala, I will send you this question in the email, and you can then answer. It's a very technical and direct question to your specific research field. So I'm not sure if it's in the interest of everybody, so I'm just going to send it to you in the email, and then you can personally answer that. Sinthandile, I hope that is in order with you. Yes, so then back to Dr. Sitole for the closing remarks, and then we can close off the session, and you can take the afternoon off with permission from me.
If only we worked for you, right?
If only.
Thank you. We are super over time, so thank you. Goodbye. No, I'm joking. So we do really apologize for going literally 40 minutes over time. But I'm going to be very quick. I would like to thank the organizers. Ilse, thank you for organizing this webinar. A special thank you to Dylan and Bianca, who really delivered. The engagement was quite amazing, answered a lot of important questions, and I think you helped a lot of people figure out how to move forward with their metabolomics research. So thank you so much. Thank you to Microsep for this. Louis, thank you so much for this opportunity and just for sharing so much knowledge with people today. I'm not sure if Professor Madala is still, oh, he is, yeah. Thank you to Professor Madala, who has a flair for the dramatic, but that's why we like him, right? Thank you, Professor Madala. Always exciting to hear you speak. Your passion just shines through when you talk about your research. So it's really, really exciting. And thank you to DIPLOMICS. Dr. Bell, thank you so much as well for being a part of this webinar today. And all the organizations, all the organizers of this webinar, and we do hope this is one in many to come, because this was really educational. And I think this is what we need to grow this field. So thank you very much. And wishing all the others that are currently in Japan representing Metabolomics South Africa, wishing them a great time. I think some of them have tried to log in and and attend today. So we're wishing them well. And more importantly, thank you to all the participants. Thank you for soldiering on. Those of you who have been online since 10 o'clock, thank you so much for staying on and enjoying this webinar. Until we see each other again. So Elsa, thank you. And yeah, you can then do the final closing and then, yeah, thank you.
Another final closing. Thank you very much. Thank you, everyone. I hope to see you soon, and I hope to see the 6 participants in Potchefstroom in August, and I hope to get so many applications that we have to convince DIPLOMICS that we need to get more than 6 people to attend. Leo. Okay, thank you, everybody. Have a great afternoon. Enjoy the school holidays. Bye-bye.